This section is named pointers. This is probably the most important section of the course. It's also probably the most difficult section of the course. The concept of pointers and C is a tricky concept, but we are going to go through it really slow. We are going to provide a lot of lectures and going step by step. We are going to start at the highest level and go into more and more detail. You have to understand pointers if you want to take full advantage of this C language. So it's very important. So let's start at the top and talk about this concept of indirection, which is essentially the same concept as a pointer. So pointers are very similar to the concept of indirection. You employ indirection in your everyday life. So for example, I'm describing what indirection means. It would be like if you had to buy something new, a new product at your company. So for example, say you had to buy a new ink cartridge for your printer. If you are working at a large company, what you would probably do is you would have to through a certain department to buy any new purchase. So you had probably go to the purchasing department. You probably would probably call somebody up in purchasing and ask them to order the new cartridge for you. It would be their job to then find a local store that provides the actual item that you want to order, and that this is the this is means is you are not going and operating that item directly by yourself. You are asking somebody to do it for you, and then through their expertise and their knowledge of who has that product in inventory, they get it back to you. So this is a level of indirections concerning you. You don't go ahead and just go down to the store and buy it. You go to the purchasing department. The person department has the knowledge that it goes and goes everything for you. This is the same concept of a pointer in programming. In programming languages, indirection is the ability to reference something using a name or reference or container instead of the value itself. We use a form of interaction by using variable names. We do not use the memory address to access data. We use a variable name. The most common form of indirection is the act of manipulating a value through its memory address. So, in addition to a really small description of indirection using a variable name to represent a memory address, you also manipulate a value through its memory address using the address itself. The address itself, so a pointer provides an indirect means of accessing the value of a particular data item. It's a variable whose value is a memory address. And this is vital to understand. We have learned variables up to this point, and that certain types of data numbers, characters, doubles, floats, and rational numbers. Now, we are going to have a variable that does not store any of this type of data. The type of data any of this store is the memory address. The memory address is going to be represented as an integer, a hexadecimal number, but it is still going to be memory address. So it's going to be the value of an address and another location of memory if it's an existing variable or a new location that you dramatically allocate. So just as there are reasons why it makes sense to go through the purchase department to order new cartridges, you don't have to know which particular store the cartridges are being ordered from. For example, there are also good reasons why it makes sense to use pointers and C. To use these variables that represent an address, a memory address. We talked about memory addresses in the very beginning of the course, and how whatever whenever you run a program and you create a variable, those are stored in memory, and that memory has a particular address. You have to know the address to get that data back, just like you need to know the address of a house if you are going driving somewhere, or address of a location. So using pointers in your program is one of the most powerful tools available in the C language. That's why it's important to understand in any program in C that is substantive is going to use pointers. So you have to understand the concept. And for programmers out there that have programmed more modern languages like Java or C Sharp, you don't necessarily have to worry about this, because all of the memory allocation and there is no real concept of pointers, even though under the hood Java uses pointers because they have copies of references. It's the same kind of concept, but in C, you explicitly have a variable that represents an address. Pointers are also one of the most confusing concepts of the C language. They tend to be abused. They tend to not be fully understood, especially by new programmers. So it's important that you get this concept figured out at the beginning and have a clear idea of what is happening as you go into more and more advanced C and more advanced pointers concept. So if you don't understand this in the beginning, study is practice writing code with pointers. The pointer has to know the type of data stored in the variable to which it points. So it's just like a regular variable, and that you have to specify the data type when you create the pointer. Now the region the compiler needs to know, this is the same region for variables. It needs to know how much data to allocate, even if you are pointing to some data. Every pointer is going to be associated with a specific variable type. It can be used only to point to variables of that type. We'll give an example of this when we talk about defining a pointer. So for example, pointers of type pointer to it can only point to a variable of the type int. Again, a variable has a value of an address. That's pointer. That address may contain a value somewhere in memory. Pointers of type pointer to float can only point to variables of type float. So here is an illustrative idea that gives you the concept of a pointer. Don't worry about the syntax here. We have briefly discussed it in previous lectures, that this ampersand and this asterisk, and you don't have to necessarily worry about that. What I want you to pay attention here is how a pointer, it has an address, and that address can contain a value but be somewhere else in memory. So in this example, we are creating a regular number. We have created a million times. When you see this syntax with the asterisk, that signifies that it's a pointer. We are going to go through that in details. You also see the ampersand, which signifies it's an address. So in this example, when we create this pointer of type int p number, we are assigning an address, because remember, pointers can only store address. And how this actually laid out in memory is you have a variable name number, and number has a value 99. Number also has an address in memory. That address in memory is the value of the pointer. So P number is a pointer that's pointing to address 1008. 1008 has a value 99, contains the variable number as well. So this is really what we are getting at. If this is not clear, you need to look at this for an hour and make sure you understand it. Again, the point is a pointer has a value to an address. That's what it stores. And then you can actually access the value in that address using certain syntax. So why use pointers? Why even approach this concept? Why can't we just use existing data types that we use and use the character array when we want to use strings? Well, accessing data by means of only variables is very limiting with pointers. You can access any location, you can treat any position of memory as a variable, for example, and then you can perform arithmetic with pointers as well, which makes things easier. Pointers in C make it easier to use arrays and strings. And we are going to go through that as well. There's another advantage to use pointers. Pointers allow you to refer to the same space and memory with multiple locations. So what this means is you can update memory in one location and then a change can be seen from another location in your program. It's a way of sort of using global data, but still having encapsulated inside functions. You can also save a lot of memory space by being able to share components in your data structures. So remember that when C was invented in the 70s, the idea of C was to be very efficient and to be low level. The idea of accessing memory directly via pointer is very efficient. It's very fast. Pointers also allow functions to modify data passed on them as variables. This is passed by reference. We are going to have a lecture on this. This is where you can pass argument to a function with your pointers, and then inside the function, when you change that data, the change will be reflected outside that function. So we no longer have to use global data. We can use data inside of a function, pass that data as a pointer, and then that data outside that function will be allocated. So it's not having the disadvantage of using global variables where everything is tightly occupied. You can limit that to only the data that needs to only the functions that need to know that data. As I mentioned, it can also be used to optimize the program to run faster and use less memory than it would otherwise, which is an important concept, especially in embedded real-time programs. Pointer also allow us to get multiple values from a function. We have talked about functions on how you can pass data functions. We have talked about how you can return data. We know that right now you can only return one value from a function. But if you use pointers, you can really return multiple values from a function. And we are going to talk about that. That's a big advantage. We are also going to talk about dynamic memory allocation, right? Now, when we create memory for a program, it's done implicitly by the compiler when you declare a variable. If you declare an int variable, it automatically creates 4 bytes for that variable. For example, when you are using arrays and you specify the size of an array, that size is allocated at compile time. So if you are trying to store more data than that, you are screwed. Your program's not going to work. But if you had the ability to actually create as much memory as you needed at runtime, that would be huge. And pointers allow you to do this. They allow you to create memory at runtime, dynamic memory allocation. We are going to be talking all about this as well. Pointers allow us to design and develop more complex data structure, and data structure is something that stores data. Example of data structure are stack, a queue, a linked list, and we create those much easier using pointers. Pointers provide direct memory access. Again, efficient, fast. Pointers are going to be big concept. We are going to have a lot of lectures on pointers. I want you guys to focus and I want you to pay attention when I talk about all these concepts because it's come back. In this lecture, I want to talk about defining pointers, mainly the syntax for declaring and then using the address of operator to access assign a memory address to a pointer. So up until this point, we should have it drilled on our head that pointer is nothing more than a variable that points to a memory address or contains a memory address as its value. So declaring a pointer is not the same as creating a normal pointer. So you don't do something like pointer. That's not the way to declare a pointer. The syntax is slightly different. You use an asterisk. So it's not enough to say that a variable is a pointer. You also have to specify the kind of variable to which the pointer points. Different variables types take up different amounts of storage. Some pointer operations requires knowledge of that storage size. So just like a regular variable, when you specify data type, when you create a variable of a pointer data type, you also have to specify that data type. You can declare a pointer to a variable of type int by doing the following: int star or asterisk p number. That is going to tell you that's a pointer. The int looks the same, but after that is the asterisk. The asterisk signifies that a pointer. And then you specify the type of the pointer itself. This is an int operator pointer. The type of the variable with the name p numbers int star. It can store the address of any variable of type int. The pointer store addresses. So if you going to store the addresses of another variable, that variable has to define as an integer type. So here pi is pointing to int variable, char star pc, that pointing to a character variable, float star pf star pg, those are pointers to float variables. That's how you are defining them. Types matter. The space between the asterisk and the pointer name is optional. You don't have to put a space there. You can have no space. What ends up happening, and we are going to talk about dereferencing a variable, is you usually use a space in the declaration. And then when you are dereferencing, you don't use it. So all these declarations should contain a space by convention. The value of a pointer is an address, so it has to be represented internally as an unsigned image on most systems. So it still has to store something. It just so happens that it stores a hexadecimal number. And even though it's storing it as it looks like an integer, don't think of it as an integer type. The same thing that you can do with integers, you can't necessarily do with pointers, and vice versa. So even though if you try to print it out, it's going to look like a number, hexadecimal number. It does not mean you can treat it like an integer. You can multiply one integer by another, for example, but you cannot multiply one pointer by another. A pointer really is a new type. It's not an integer type. The %p represent the format specified for pointer. I'm going to go through displaying the different data for a pointer, and we'll see how that's used. The previous declaration creates the variable, but there is no initialization, there is no assignment there. You always want to assign a value to a pointer. It's very dangerous if you do not initialize that. So you want to initialize a pointer when you declare it. If you don't know what to initialize it to, if it's not memory available address or you didn't allocate memory dynamically for it, you can use a null pointer. So you can initialize a pointer so that it does not point to anything. You do this using null. You say int star p number equals null for a pointer to an int. Null is a constant that is defined by the standard library. It's the equivalent of a zero for a pointer. It means that it does not point to anything. It's guaranteed not to point to any location in memory. So this is good. You want to do this because what it means is you are not going to make any mistakes by accidentally doing a buffer overflow. So writing to memory that you are not supposed to write to, by initializing it to this, it actually limits some mistakes that you can make. We talked about null a bit previously. We talked about the null character. That concept is really different from the null pointer. A null pointer means it's not pointing to anything, and it should be initialized with that. You need to add an and include directives for standard df.h. If you want to use the null definition here, the address of operator, if you want to assign your pointer to address, you can use the address operator of an existing variable. So if you want to initialize your variable with the add or sub variable you have already declared, you use the address of operator ampersand. We have seen this when we have discussed the scanf function. Here we are assigning an integer value, variable 99. We are creating a pointer of type int, and we are assigning it the address of number. We can do this because number is an int, and the pointer that we created is also pointing to an int. So all we have to do after the equals operator is using the ampersand. And so now p number is going to contain the address of number. Initial value of p number is the address of the variable number. The declaration of number must precede the declaration of the pointer that stores its address, because you cannot assign to a pointer something that does not have memory allocated. If you try to assign to that pointer number does not exist unless you do it after. In order to assign an address to a pointer, that address has to have memory allocated for it. Otherwise, the compiler is going to complain. Be careful though, because there is nothing special about the declaration of a pointer. You can declare regular variables and pointers in the same statement. So you could say double value, p value, fnum. In this statement here, this is the only the second variable, p value, is a pointer. The other two are just double. That's a little bit more explicit, a little more obvious in that declaration. But what if you say in star pq? This implies that they are both pointers and they are not. We only have one int pointer here, that's p. The variable q is just to type int. It's a common mistake to think that both p and q are pointers. So be careful when you are declaring a pointer on many variables on the same line. It's also a good idea that a variable is a pointers by just looking at it. So usually you do all your declaration of variables at the top of the program, usually inside the main function. And when you see those variables used later in the program, you can easily identify the different data types or the different pointer types because they have a p as a prefix. So this lecture just went over how you can declare a pointer, and then assign an address of an existing variable to a pointer. Now there are cases when you don't want to necessarily assign an existing variable a value of pointer. Maybe you want to allocate new memory. We are going to talk about those in the subsequent lecture, but right now we are going to keep it simple. We are going to focus on the using pointers of type int, different EG types like doubles or floats. And we are going to concentrate on assigning existing variables the address of and see how that works. Memory addresses. That memory address actually contains a value of somewhere. So pointers point to that memory address. I want to get the value of what it's pointing to, because I would just print out the value of a pointer that would be an address, but I want to get the address. I want to get the value of the address. So you can access the value of an address that a pointer is pointing to using the indirection operator. The indirection operator is the asterisk. So we learned how to use the asterisk to declare a pointer. We are also going to use the asterisk to find the value that a pointer is pointing to. Sorry. So it's also referred to as the conference difference operator, because you use it to difference a pointer. So for example, if you have a number, it's equal to 15, you declare pointer of type int pointing to an int, and you assign it the address of a number using the ampersand. Now, how do you get the value of what pointer is pointing to? You can dereference it. You can basically, what the value that the pointer is pointing to is the value is 15, because it's pointing to the address of a number which is 15. So the pointer variable contains the address of the variable number. You can use this in an expression to calculate a new value for the result. So say we wanted to do result equals the value that the pointer is pointing to plus 5, you would use the asterisk for it before the name of the pointer. And so what this would do is it would basically say what is pointer variable pointing to. It's pointing to 15 and 5 to it. It's the address that the pointer is pointing to. What is the value of that address? So the indirection operator asterisk, you should notice, is also the symbol that's used for multiplication, and it's you also used when you declare pointer types. So this can get very confusing. How do you know necessarily? Sorry. What's going on? How does the compiler work? Well, it is all about context. It depends on when you use that asterisk and where you use it. If you use asterisk when you declare a pointer right after the type of the pointer, then it's obviously using a declaration. If you use asterisk in between two numbers, then it's being used for multiplication. And if it's used right before the pointer name on the right hand side, for example, or the left hand side, it's going to be assigning a value or accessing a value. So it's all about context when you use this indirection operator. And that's how it works. So that's how the compiler is going to interpret it. Whenever you see it in this example, star pointer, and you don't have a data type before, or you don't have two numbers on each side, then you know it's an indirection pointer dereferencing. So let's go through an example. Here's another example where we are going to create an integer count equal to 10. We are also going to create an integer of type named x, another variable. We are initializing count to 10. X is initialized to nothing. When then create an int pointer, we know send int pointer because we have the asterisk after the data type, and then we named it int pointer. We are now going to assign to that int pointer the address of count, because remember, pointers only contain addresses as their values, but they also are pointing to something. So we can then assign the variable x whatever int pointer is pointing to. What is the value of the address that is contained in pointer? So x is going to actually display 10. So if we go ahead and display that saying count %d, and x %d, count is equal to 10, x is going to equal to 10. That's how you can dereference a pointer and get the value that it's pointing to. If you want to display the pointer's values, because remember a pointer has a value in memory, it's just an address. So what if you want to display pointer's value, which is represented by a hexadecimal number, integer, and address. Well, you can use the format specifier %p. We talked about this before. This will output a pointer value as a memory address in hexadecimal form. So if we were to do something like this, where we declare our number, we declare our pointer, we initialize it to null, because that's good practice. We want to always do that. Whenever you are not assigning something in a declaration to the pointer, make sure you initialize it to null. We then assign our number variable 10, and then we assign our pointer to the address of number. So the value of p number is actually going to be an address. So if we were to try to print it out, we would use %p, and that would be the value of the address. If we wanted to print out what it's pointing to, we would have to dereference it using the indirection operator. But when you print out the address, what it does is it prints it out in hexadecimal, and pointers occupy 8 bytes in memory, and addresses have 16 hexadecimal digits. So how does that work? Well, it depends on whether or not your machine supports 64-bit or 32-bit addresses. If your machine has 64-bit operating system, then you are going to see 16 hexadecimal digits. If your machine or your operating system only has 32-bit addressing, then you will see the hexadecimal represented as 8 hexadecimal digits. Now, what if you want to display an address? You may say, what's the difference? Because the pointer has a value, but you can also deploy the address with the address of operator. So in this example, we want to display the address of a number. Number is not a pointer. Number is just an integer. Sorry. If we want to get the address of that, we use the ampersand. If you want to display the address of that, you just use %p again. You just apply the ampersand. So if we supply the ampersand with the pointer variable, we would actually display the address of that pointer, not the value of the pointer. Remember, the address of the pointer is some address in memory. The pointer value is an address that it's pointing to, and the value that it's pointing to is somewhere else in memory. So remember that illustration where we showed how pointers work. A pointer, when you declare it, creates memory for that pointer, 8 bytes. The value of that pointer is an address. And then whatever that pointer is pointing to is a value, usually of the type that you provided. But remember that there's really 3 parts of it. If you want to print out the p numbers, addresses, you again would use the ampersand. That would be the address of the actual pointer. And you would have to use the void star to get around a warning. So remember, a pointer itself has an address just like any other value. It gets allocated when you declare it. You use %p as a conversion specified to display address. You use the ampersand, the address of the operator, to reference the address that the p number variable occupies. That's the address of the pointer. Then again, the pointer has a value of an address. The cast void is to prevent a warning from the compiler. Specifically, the %p specification expect the value to some kind of pointer. And so you have to cast it displaying the number of bytes a pointer is using. Another way to get information about a pointer, and another way to get information about a pointer is that here you can use the size of operator. We have learned about the size of operator to display different data types, bytes. You can do the same thing with the pointer. on a machine that I am running. This will occupy 8 bytes, and the machine address has 64 bits because it's a 64-bit operating system. And you may get a compiler warning when using size of this way. Size is an implementation defined integer type. To prevent the warning, you could cast the argument size %d bytes, and you would say int cast it to an inch size of p number. That's going to give you the size of the pointer in memory, size of pointer of that address, which again is 8 bytes on most systems, because that's just contain an address. Another example here, this is going to display a number of things, and we'll run this example to show the output. But just before we run it, I want to describe a little what's going on here. We have a number that declared, we have a pointer that's initialized the null, we set the value of number to 10. Sorry. And then what we want to do is we want to print out the address of the integer number, and we want to print out the value of number. Very simple, using the address of operator and then just the variable. When we do the address of operator, we do %p. We are then going to assign the address of number to our pointer. We are then going to print out some pointer information. We want to output the address of the pointer itself. We can just use %p, void star and %number. We want to see how many bytes that pointer has in memory. We can say size of. We want to see the actual value of the pointer, which is an address. We can just say p number without any extra information, and then we use %p. If we want to see the value that the pointer is pointing to, the value at the address, then we do *p number. We use the indirection operator, and we know that p number is pointing to an in, so we can say %d. So let's take a look at this example in code blocks to see how it actually displayed. What we are going to see is some hexadecimal number for addresses whenever we display addresses, and we are going to see values in other cases. So this should look familiar. This is just a program that is showing you how to access different parts of a pointer. So again, we have a regular number data type int, and we have our pointer. We initialize it to null. We are first going to display our number, which is 10. So this is going to display the address of number. And then it's going to display the value of number on line 10 and 11. We are then going to assign our pointer the address of number. If we want to see the actual address of our pointer, we just use the ampersand, the address of operator, and we cast it to void star. We use %p. If we want to see how many bytes the pointer is in memory, we do %d size of. If we want to see the address, then value of p, the pointer, we do %p, and we just say p number because p number is an address. If we want to see what the pointer is pointing to with the value of the address, that's in the value of pointer, we just say *p number. We dereference it, the indirection operator. So let's run this. When I run this, you will see the first two things that are printed out. The number's address, which is on line 6, and that's some hexadecimal number 0060FF0C. And this is actually number running a 32-bit program, so you see only 8 bits. The number variable, which is 10, we then print out the address of the actual pointer to allocated memory. It's a different address than number because this is the address allocated for the pointer. The pointer number size is 4 bytes, and that means it's a 32-bit address. The pointer's value, which is in the address of number, it should be the same, and it is 0060FF0C. And you see that you can actually get the number addresses by just using the name, the pointer with %p, we show size of operator 4 bytes. If you want to get the value that p number is pointing to, which is 10, you have to dereference it using the indirection operator, and you see what it's printed 10. But you see, you use %p whenever you are displaying addresses. Use the %p when you are displaying values of the integer pointer or the number of bytes. For this, use %e. So this is the basic syntax of accessing pointer values. Address of pointer ampersand value that the point is pointing to, just the name of the variable, and the value of the pointer itself is just the name of the variable. Then the value that the pointer is pointing to, use the indirection operator. Section on pointers, this is going to be a challenge that gets you acquainted with the pointer syntax. Mainly, you are going to create initialize a pointer, assign an address to a pointer, and then display some of the pointer's values. So in this challenge, you are going to learn how to create, initialize, assign, and access a pointer. Creating the pointer is just declaring it. Initializing it will be you initialize it to null, because it's not going to point to anything. And that's how you can do. Assigning it, you will assign it to the address of another variable. And then assigning a pointer is using the indirection operator, the difference operator. So write a program that creates an integer variable with a hard-coded value. That's pretty easy. We know how to do that. The reason you have to create the integer first is because that's going to have a memory location that's are going to, and once you have that integer variable created, you then want to create a pointer, initialize it to null, and then assign the address of the int to the pointer. Using the address of pointer operator, pretty straightforward. I want you to display as output the address of the pointer. The address of the pointer is just when you declare the pointer. The pointer has an address in memory. You will need to use the address of operator to display the address of the pointer itself. Then I want you to display the value of the pointer. The value of the pointer is going to be another address. It's going to be an address of your integer variable. And then lastly, I want you to display the value of what the pointer is pointing to. The value of what the pointer is pointing to, you have to use the dereference operator, the indirection operator. These are the three things that a pointer can be equal to. You also have to understand what format specifier to use in each case. Typically, you will use a certain format specifier for address, and then you will use a different format specifier for whatever the pointer is pointing to. This is a basic assignment to get you familiar with the syntax of a pointer, and also understand the different values that a pointer can store. Again, mainly the address of the pointer itself, the pointer's value, which is an address to some other location, and then the pointer's value of what's pointing to from that address, which would be the value using the indirection operator. So good luck. I will provide you a solution to get you familiar with the simple syntax. Hopefully, this would not take you too long, but it's good little exercise to help you. I want to talk about the use case for pointers when we are going to use them, how we are going to use them. We know how to create them, declare them, and define them. We know how to assign an existing variable's address to the, and we know how to dereference them, how to get the value that the pointer is pointing to. Now, how do we actually start using them? So C offers some several basic operations that you can perform on pointers. You can assign an address to a pointer, which we have learned about already. This is an existing variable where the variable has an address, and you just look at that variable address by using the address of operator, and we have a point to that. We could also assign an existing pointer to another pointer. That's two ways you can assign an address to a pointer. So it can be an array name by itself. We have not talked about arrays yet, but when you assign a array to a pointer, all you have to do is specify the name. You don't even have to use the address of operator. So far, we have just focused on using an existing variable and passing in the address of the variable itself. But the three way you can do it are mentioned there. You can also dereference a pointer. We just learned about that where you use the asterisk, the indirection operator. This will give you the value that's stored in the pointer too. The pointer's value, which is an address that's the pointer is pointing to, just use that. You can also take a pointer address. This is the actual address of the pointer when you create the pointer. Where the pointer itself is stored, you can use the address. I have operator on that point as well. And you can also perform pointer arithmetic. We are going to have a separate lecture on this. This is where you can use the plus and the minus operator to either add integers to a pointer or subtract integers from a pointer. And this allows you to have a specific notation and allow you to jump around in memory quicker, especially if you are using array. So what you typically do is when you add an integer to a pointer, using the plus operator, it's going to just set the address of that pointer up so many bytes. If you subtract a number from a pointer, it's going to set that address in minus a certain number of bytes. You can also increment, decrement by one, and you will see this is very common when we use it in arrays. So when you are in an array and you want to move to the next element instead of using the index, you can use a pointer and just increment it by one. If you want to move to the previous element instead of using an index, you can just decrement it pointing by one. So pointer arithmetic, we are going to talk about exclusively, but that is something that you can do with pointers. And again, it's particular notation that allows you to move around quickly in memory, be more efficient. You can also find the difference between two pointers. So if you have two pointers and the elements are in the same array, you might maybe want to find out how far apart they are. The elements, you can minus them. This would be the difference of two pointers. And so if you are index 5 and then you are at a pointer pointing in index 5, you had another pointer pointing to index 15, you could minus them, and that would give you how many elements they are away. Because it would be the hexadecimal address minus the other hexadecimal address, assuming the array in continuous memory, which it will display how far apart they are. You can use relational operator to compare the values of two pointers. Pointers have to be the same type. So if they are both pointing integers, they both have to be the same type. This is just going to tell you whether or not the address are greater than or less than. Again, you could identify which part of the array you are in. There are also two forms of subtraction. So I just talked about subtraction where you can actually take one pointer and subtract it from another one, which you will get a pointer, or you can subtract one pointer from an integer, which will give you a pointer. So subtract one pointer from another to get an integer, or to subtract an integer from a pointer to get a pointer. These are the two cases. So we will keep in that mind, we will go through some more examples. Be careful when you use the incrementation or decrementation of pointers and using the array out of bounds. So most of this stuff that you do with pointer arithmetic is when you are operating on arrays, because again it allows you to move quickly. It's simple syntax, but remember the arrays have an out of bounds error. So if you increment too far, you are going to go out of bounds in the array. If you decrement too far, you are going to have an under bounds. You are going to a negative number. The computer itself is not going to keep track of whether a pointer still points to an array element. So using the point of arithmetic on array, you got to be careful. If you want to pointers used in expression, you can also do that. So we talked about this a little earlier, and we dereferenced the pointer and we added 15 to it. I think we got 20. So the value of pi pointer can be used in arithmetic expression. So if a variable is defined to be of type pointer to integer, then it is evaluated using the rules of integer arithmetic. And we showed that with the dereference. So if you have a pointer and you have a pointer, initialize it to null, you then sign your pointer that variable address, you then can just say star p number plus equals 25. Remember, star p number is getting the value of that's pointing to. So what this is doing is it's saying the value of p number equals the value p number plus 25. So the value is going to be equal to 35. This is not changing what it's pointing to because we are using a strict. So it is not changing the address that we are pointing to. It's not changing the address itself because we don't have the address of operator. We are changing the value that it's pointing to. So incrementing the value of the number variable by 25, the star indicates that you are asking the contents which the variable called p number is pointing to. If a pointer points to variable x, that pointer has been defined to be a pointer to the same data types as x. So if you create an end pointer, a float pointer, you can only have an address of a data type that is float or int depending on which one you declared. So the use of the indirection operator in an expression is identical to the use of x in the same expression. And that all it's saying is if you use a float or you have an int and you use the indirection operator to dereference it. You can do whatever you can. If you had a float in it, whatever it's pointing to, a variable defined is a pointer to an int can store the address of any variable of type in. We know that. So here int value equals 999. We can assign an int and then we can add to it. The statement will operate with the new variable value and the new content value will be 1024. P number is pointing to value. The address of value. So if you use the pointer that it's pointing to value, you are going to change the value of this variable value. So just remember that this is the concept of changing a variable in one spot, the pointer, and you are changing it in multiple variables. A pointer can contain the address of any variable of the appropriate type. So you can use one pointer variable to change the values of many different variables. There are ints or doubles or floats. As long as they are the type compatible with the pointer type, you can change that value. You can't change p number value. If p number is pointing to a float and the value is an integer, you would not be able to do that. You would have a compile error. Another example here we are going to show you how to get the address of some variable. So here in this main, we are doing some pointer arithmetic on the actual expression. So we are not doing anything on array. We are not incrementing or decrementing pointers in that. So we are decrementing values. So we have two long types, num1 and num2, and then we have a pointer of type long. We initialize it to null. We assign the address of num1 to our pointer pnum, and then we assign the value of pnum to L. So that means num1 is now going to be 2i. If we increment num2, now num2 have not done anything to yet. So value of pnum is 2i. That means the value of num1 is 2i. L is just the suffix to signify that it's a long. If we now increment the long num2 value 0i, it's going to be 1l. If we say num2 plus equals star pnum is 2i, so it's going to be 1l plus 2l. Number 2 is now going to be equal to 3i. And then if we assign the address of num2 to pnum is now going to be equal to the address of the num2. So if we increment pnum, what we are pointing to, we are now going to have 4i. And for L, and we'll look at this inside of code blocks, but I'm walking you through it. Num1 is going to be equal to 2L, num2 is going to be equal to, it's pointing to pnum. Pnum's 3L, so I think it's going to be 3L. Pnum is going to be 3L, and then pnum plus num2 is going to be 6L. So let's see if I'm right. Go through this in code blocks. So here we are in code blocks. Try to go through this by hand. But now we want to see if we are right. Let's use the debugger. We'll put this right here and we will see as we go through the program how values are changing. So let's build this and let's debug it. This is going to start up and it's going to stop at line 10. And if we bring up our watch window, which we can do by doing to debug in Windows watches, we can see the values as they are going. So right now, num1 is 0, num2 is 0, pnum is pointing to null. That's why it's 0 into 0. Because we know that null represents 0 in p number. So after we execute line 10, pnum should now have the address of num1. So let's just step over. Now pnum has an actual address 0 into 60ff08. After we execute line 11, we are going to say the value of pnum is equal to 2l. And we are not going to be actually seeing anything in the watch window for that. But let's go ahead and execute it. Pnum still has the same address. Num1 is now changed through because pnum had the address of num1 and we changed it. So now num1 is 2. Now in lines 12, we are going to increment num2. So num2 is just going to become 1l. It's going to be 1. The address of pnum is still the same. Now we are going to add to num2. Whatever pnum was, pnum remember is pointing to num1. So num2 should be 3. Then we go to 14. Num2 is 3. Num1 is still 2. Now line 15. Now on line 15, pnum equal to n num2. We are going to assign a pnum a new address of the num2. So after this, we are no longer going to be 0x60ff08, that is hexadecimal. We are going to be this hexadecimal number. So now if we increment the value that pnum is pointing to, which is number 2, and number 2 is 3, number 2 should now be 4, and we see it's 4. Now we are going to print out all these values, and you are going to see the value of num1 should be 2. The value of num2 should be 4. Pnum is pointing to num2, so that should be 4 still. And then we are going to say the value of pnum, which is 4 plus num2, and which is 4 should be 8. So I might have actually been off with 6. So now we would not be able to see that in the watch window. So let's just play it and see the output as printf statement. We should see 2448. So it's run this now in non-debug mode, and we see 2448. So there we go. I hope that made sense. Let's go back and continue our discussion. So how about when we receive input? How can we use pointers in that way? So far, when we use scanf to input values, we have to use the ampersand operator. Whenever we have an enter or float data type, the only time we have it is when we had a character array, and the reason for that is because character actually is a character pointer, which we are going to talk about. But if we use scanf to input values and we use them on normal data types that are not character arrays, we have always had to use this add or sub operator, and the reason for that is scanf second argument is a pointer. So we have to send it an address. Pointers only have values of addresses. So when you have pointer, that already contains an address. You can use the pointer name as an argument for scanf. So now you don't have to use the ampersand operator if you actually created a pointer, because the second argument to the scanf is a pointer. And so you can just say the pointer name in the past. If we wanted to store a value in value, we would have say ampersand value in the scanf second argument. But if we have a pointer that we create and it already points to an address, as it does in this example, then when we use scanf, all we have to say is the name of the value, the name of the pointer. So here is a case when we have an integer, but we don't have to use ampersand because we have a pointer to an integer. We just say %d p-value. So there are other times when you can pass in regular names of variables to scanf besides character arrays. If you have a pointer, you can also print out what they entered afterwards, and you will notice that value is actually going to be changed to whatever they entered, because we are pointing to that address testing for null. There is one rule that you have to burn into your memory. This is very, very important. We talked about dereferencing, but what happens if you dereference an unintentionalized pointer, a pointer that's pointing to nothing, or a pointer that does not have memory allocated for it? So what if we do something like this? We declare a pointer, but we have never actually initialized it, and then we try to assign to it. We dereference and assign to it. That's a big mistake. So the second line basically means that you want to store the value 5 in the location to which point pt points to. But pt does not point to anything because it has not been initialized. So pt is now going to have a random value. So there is no knowing where 5 will be placed, so it could be placed anywhere in memory. This might be harmless, it might overwrite existing data or existing state variables in your program. It might cause the program to crash. It's very problematic. So when you create a pointer and you allocate memory to store the pointer itself, it does not allocate memory to store the data. So by saying star PT that allocated memory for the pointer, but it did not allocate any memory for what? For the value of the pointer, the address. Remember, pointer contain address. It created the pointer, but it didn't create any memory for what it's pointing to. So you can't dereference it. So it does not allocate memory to store the data. Before you use a pointer, it should be assigned a memory location that has already been allocated. Or you have to use dynamic memory allocation using malloc, which we'll talk about. So you either assign the address of an existing variable to the pointer, or you use malloc, which is dynamic memory allocation. But keep that in mind whenever you use a pointer. If you created it and it was null, you want to check it for null beforehand. We'll talk about that in a second. But if you created a pointer was not initialized, do not assign anything to it unless it's either pointing to another variable initialized that way or having memory allocated. So this is where null comes into play. You can actually test for null to make sure you don't have a dereference error, make sure your program does not crash. So we already know that null basically points to nothing, and we should initialize all of our variables or pointers to null. So we should always do something like this. Null is a special symbol in C that represent the pointer equivalent to 0 with ordinary numbers. The below also sets a pointer to null using 0. So we can also, if we don't want to pass it or assign it to a null, we can just say 0. And that's the equivalent of saying pointing to nothing. So because null is the equivalent of 0, if you want to test whether p value is null, you can do something like using explicit test. You can say pointer equals null, and if pointer is equal to null, meaning it's 0, then you can actually do something. So if it's not 0 or not equal null, it's 1, true, or any other value. That's a way to check against having crashes. You make sure before you actually try to dereference something, this will tell you whether or not it has memory allocated. So you want to check for null before you dereference a pointer, and you often do this in functions because functions will take pointers as parameters. And if the caller is passing in bad data or passing in pointer does not have any memory allocated, it could crash your code. So what you want to do is you want to make sure that the caller has a valid address so you can check it for null. Basically, what this means always to have these if checks to say not p value or not pointer. And if it is not pointer, then you can dereference it. We are talking a lot about pointers. We have discussed quite a bit. I'm sure it's getting a little overwhelming. You may want to take a break and go through the previous lectures. Try to really sink this concept in your head. Pointer just contain address, but there's three part to it, so it can get problematic. But stay positive, keep with me, and I know it's confusing. We have talked about working with address. We have talked about working with values. We have talked about working with the pointer itself. And we have talked about working with variables that point to pointer. So there is all this stuff you got to remember. And it can be very, very overwhelming and frustrating. And it's always hard to try to figure out what's going on. And it's going to take a lot of practice. The best way to understand this concept and everything we talked to up until now is to practice, write short program that use all the concepts I mentioned. So I write a program that gets the values using a pointer. This would be maybe using the indirection operator, dereferencing, write a program that changes values using pointers. So this would be dereferencing, getting the values using pointers and just the same of the pointer, which would be the address. Printing address, we have looked through all that syntax. Practice this step over and over and over again. That's how you are going to get good at it. You have to get your confidence up and you have to study these concepts in detail to master them. We still have a lot more to talk about pointer, but this may be it must means you can't change the value of a variable. But what does it mean? When we apply it to a pointer, so when we use the const modifier in a variable or an array, it tells the compiler that the contents of the variable array will not be changed by the program. The alternative was to create define statements by the preprocessor, but const is usually more efficient, better way to do it. With pointers, we have to consider two things. When using a const modifier, are we actually saying that the pointer cannot be changed, or are we saying the value that the pointer points to cannot be changed? Because remember, a pointer contains a value of an address and we may not want to change that address ever, or we may not want to change the value that the point is pointing to. In either case, we have to be specific in our syntax. So we may not want to. So you can use the const keyword when you declare declare a pointer to indicate that the value pointed to must not be changed. The way that you provide this and again so the pointer is a value as a value has an address. What it's pointing to is the value of that address. If you want to have that not change, you would do something like this. You would say when you declare the pointer, you would put the asterisk in the constant modifier before the type. So you would say constant whatever the type your pointer is asterisk pointer. So this is actually deformed defining a pointer to a constant. We are not going to be able to change 999 L. So we declare that the value pointed to by the p-value to be constant. The compiler will check for any statement that attempt to modify the value pointed to by the p-value. And if there's anybody that does in the program, it's going to throw an error. So this is the syntax. Again, what you want to notice here is the const is the first word and it's before the type. So that's saying that the value pointing to cannot change. So if you try to do something like this on p-value, you try assigning a value to what's pointing to, because you see the indirection operator there. That means we are assigning a value to what we are pointing to. If we try to do that, it's going to give an error because we can't change that value, can't change 999L to 888L. So now what about pointers to constant? And in the previous declaration, we created the pointers that the point is pointing to that cannot change, but we can still change the actual value of the variable that we declared. So we would still be able to change long value. We can't change star p value, but long value is not defined as a constant. It's just defined it as a long value. So we can still modify the long value integer pointer because it didn't have constant applied. We only applied constant to the pointer. So we can say value equals 777L. The value pointed to has changed, but you did not use the pointer to make the change. The pointer set is also not a constant. The pointer, remember, contains an address. We did not declare the pointer to be constant. We what the pointer is pointing to be constant, so we can still change that as well. So if we declare a new variable called number, we can say p value equals the address of that number. That's perfectly fine because we are changing the address of the value of the pointer. We are not changing the value of what the pointer has was pointing to. So understand this distinction: either changing the value of the pointer, which is just an address, or changing what the pointer is pointing to. If you don't want to change what the pointer is pointing to, const has to be that first keyword in the declaration of the pointer itself. So again, in this example, we are going to change the address stored in p value to point to a number. We still cannot use the pointer to change the value that is stored because that was declared as we can't change that value. You can change the address stored in the pointer as much you like, just like we did. Using the pointer to change the value pointed to is not allowed even after you have changed the address stored in the pointer. So even though we just changed it to long number, the pointer still had constant as the keyword. So we can't change the value no matter what the pointer is pointing to. What about not allowing the address of the pointer to change the value that's in the pointer? So you also may want to ensure that the address stored in the pointer cannot be changed. You can do this by using the constant keyword in the declaration of the pointer the same way, but it's slightly different. Instead of having const as the first keyword, you put it after the data type and after the asterisk. This is saying that the pointer itself cannot change its value. If you put it before the int, you are saying the value pointed to by the pointer cannot change. So when you do this, it ensures that the pointer always points to the same thing. The address will never change. The compiler will check that you not inverting attempt to change the pointer elsewhere in your code. You can't change this address. So if you try to say p count equals and item, you would get an error because that can only ever point to the count address. It's all about where you place the constant keyword if you want to change. If you do not allow the address of the pointer to change, constant as the first keyword does not allow the value to the pointers pointing to be changed. If you put the constant after the data type in the star, that's saying the pointer addresses cannot change. So that's a lot to take, and that's a very confusing. So study what I just said. Understand that syntax. It's very important and it's very tricky. It can be very easily make that mistake. So understand the difference. You can still change the value that p count points to using p count, just like we could in the previous one, because p count is even though we can't assign a new address. We can still change the value that's pointing to. So we can dereference it and change it to what the pointer and changes the value to 345. You can create a constant pointer that points to a value that is also a constant. So you could do something like this: constant in a star, constant p item, and that's saying what the value is pointing to is constant. And the pointer itself is a constant. So p item is a constant pointer to a constant. So everything is fixed. You cannot change the address stored in p item, and you cannot use p item to modify what it points to. However, you could still change the item. Item is not a constant, so you could change item. You can change the value directly. If you wanted to make sure nothing was changed, you would have to actually create the item int variable as a constant as well. And then what would say it's never going to ever change. But remember, the difference here between constant pointers and constant values that the pointer is pointing to, you can use both, you can use one or the other if you wanted to ensure that everything. Mainly, if we don't want to return any data from a function, we use the void as a part of the function signature. What about when we use void pointer? What does this mean? Well, the type name void means absence of any type. So a pointer of type void star can contain the address of a data item of any type. So it has a lot of flexibility. If you don't know what you are going to store as a pointer, you can say void star. Pretty good. It's usually used in functions for or a return type with functions that deal with data in a type independent way. So you can allow your function to be more flexible if it takes void star pointers. It basically means that your function can take more than one type of variable, expect, except it's not completely flexible because you have to cast it some way when you dereference it. So any kind of pointer can be passed around as a value of type void, any type. The void pointer does not know what type of object it is pointing to. So you cannot dereference it directly, and that's where the real thing comes along with the void star. It's great for long flexibility for different data types, but you can only use it if you know the data type. So you have to provide an explicit cast to the pointer when you dereference it. The address of a variable of type int can be stored in a pointer variable of type void because void star means that any type of data can be stored inside there. So when you want to access the interval value at the address stored in the void star pointer, you have to first cast it to a pointer of type int. In this example here, we are going to see how you use the void star pointer. We have three variables. We defined an integer and a float and a character. We are now going to create a void star pointer. Because the pointer is of type void, we can assign it. The address of which is an int I, we can assign it the address of f, which is a float, and we can assign it the address of character or ch, which is a character. The only problem is when you dereference, you have to know that type, but you still see the advantage here. The advantage here is we only have to create one variable type and we can store multiple different addresses in it. But whenever you want to use it, you have to use that in a star. And you will see here when we are printing out the data that the in star is casting the pointer and then we are dereferencing it. The star outside the int parenthesis is dereferencing. So that's going to print out the value that we pointer is pointing to, but first it's going to cast it to the right type. So in all three of these v pointers, it's going to print out for the int, it's going to print out 10. For the float, it's going to bring out 2.34, and for the char, it's going to print out k. We'll see the void pointer and more in the function parameter, like I said in return types. That's really want to talk about the relationship between pointers and arrays. There is a strong relationship and we need to understand this relationship before we can actually talk about pointer arithmetic. So let's get started. An array is a collection of objects of the same type that you can refer to using a single name. We know that we are pretty good at arrays by now. We have been using the character array for a few sections now. It's an array you can access by using an index or subscript inside those brackets. We remember that. We know that arrays are zero based. They start at zero. But again, It's just a way to hold multiple months with the same variable name. A pointer is a variable that has its value, a memory address as its value, and it can reference another variable or a constant of a given type. We also should at this point be pretty clear on what a pointer is. It just holds a memory address. You can use a pointer to hold the address of different variables at different times, but you have to have the same type. An int pointer has to point to restore the address of an int type. Arrays and pointers seem quite different, but they are very closely related and can sometimes be used interchangeably, especially with the character array. You can actually create a character, remember which is a string, and you can create a character pointer, which are essentially the same thing. There is only slight difference whether or not you'll allocate memory and free it with a character pointer with a character array. You don't have to do that. But a character A is also fixed size. So if you create a character array string with 20 as its size, you can only store 19 characters. With the character pointer, you can use dynamic memory management and you can have the size increase or decrease. It can be more efficient concerning memory, but one of the most common use of pointers in C is as pointers to arrays. This is when you most often use pointers, especially to characters. Character pointer is the same as a character array. The main reasons for using pointers to arrays are one of notational convenience and of program efficiency. So you can use either an array or a pointer in many cases, except when you are talking about dynamic memory management. But in most cases, you can, and really the only difference is its syntax. It's the notation. It's whether or not you use a subscript to access an element, or whether or not you use point arithmetic, whether or not you use the character pointer to point to the specific address of that element. It's also more efficient to use character pointers as well. Pointers to arrays generally result in code that use less memory and executes faster. So you want to use a pointer for characters as much as possible and a pointer to other data types as well. Because it is faster and less memory use, pointers over arrays for the most part. If you have an array of 100 integers, we know what this means. You just say int value is 100, 100 is the size. That means you can store 100 integers in that array. You can also define a pointer. We are going to name it values pointer since it's pointing to the values array, and it can be used to access the integers contained in this array. So we just say int star values pointer. We know how to declare a pointer at this point. When you define a pointer that is used to point the elements of array, you do not designate the pointer as type pointer to array. Up until this point, all we have ever heard about is pointer to end, pointer to double. But when you are using array, you don't say pointed array. That actual pointer is pointing to a specific element contained in the array. So keep that in mind. It's not actually entire array when you clear a pointer with the address of values. So to set the values pointer to point to the first element, the values array, all you have to do is say values point or equals values. You don't have to put the address there or anything, because values array is a pointer. That's what you have to drive in your head is all these days are pointers underneath the hood. So if you want to assign the first element of an array to a pointer, all you have to do is specify the array on the right hand side of the equals operator, and on the left hand side you just have the values pointer. This is going to point to the first address in the array or the first element. The address operator is not used. Notice that the C compiler treats the appearance of an array name without a subscript as a pointer to the array. So specifying values without a subscript has values. And so what this means is you can now point to subsequent values in the array by just incrementing the pointer to go to the next address. And that's what we are going to talk about in the next few lectures when we talk about pointer arithmetic, and it's just a notation thing and it's also an efficiency thing. So an equivalent way of producing a pointer to the start of values is it is to also apply the address of operator to the first element of right. So you can do it also ways, either way is fine, but you can you could also do this. You could say value pointer address of value sub 0, that will set the value pointer to the first element in the array. So you can use this one, or you can just say values points equals values. Obviously without the ampersand and without the subscript, it's a little more less code or easier to write. This may be a little more clear because you don't necessarily know that values is an array unless you look at the declaration. But again, either way is fine. Values pointer equals values, or values pointer equals address of value sub 0. It's a matter of programmer preference, and again it's a notational thing. Just to reiterate, when you have two expressions, uh, index I and asterisk or plus I, those are equivalent in meaning. So we just want to make sure that you understand this both work. If the name of an array, you can use the pointer and you can dereference it, and both work if it is a pointer variable. Use an expression such as AR plus plus only works if AR is pointer variable. So you can't increment an array by saying plus plus and expect it to go to the next element. You can only do that in array pointers or pointers. So if we have a AR that's pointer pointing to array and we want to go to the next element, we can just increment it every time. But if you say index I, because or index I is an array and an array is a pointer, and you can dereference it by saying AR, which is AR is a pointer, we have assigned plus I, it's the same thing. So in the next few lectures, we are going to talk about pointer arithmetic, and this strongly relates to the relationship between arrays and pointer. Pointers can be arrays. It's not a pointer array, it's an element. So you can use the address of a pointer to navigate through an array, iterate through an array. Hello and welcome back. In this lecture, I want to talk about pointer arithmetic. Now that we understand the relations between arrays and pointers, this concept is going to be easier to understand. We say arithmetic, but we don't really means is you can do either plus or minus or incrementation or decrementation on a pointer itself. So the real power of using pointers to arrays comes into play when you want to sequence through the elements of an array. You want to go from the first element to the end. You want to iterate through them. This is the real power pointers, because pointers point use address its element in array is just another address. So you can just do plus plus or pointers and you can go to the next address. So here values pointer can be used to access the first integer of the values array. It can be used to access values index 0. So if you remember, values pointer is a pointer that pointing to an integer array, and we assign it to the first element in the array by just assigning the pointer to the array name. We could also use the address of operator index 0 if we wanted to. But when we dereference values pointer, because it's pointing to the first element in the array, it's going to give you the first integer in the value index 0 array. If you wanted to dereference values index 3 via the pointer available, all you have to do is add 3 to the values pointer and then apply the indirection operator to dereference it. So you could just do something like this. You can say values pointer plus 3 and then dereference it with the asterisk. And you usually put the asterisk outside of quotes to make it clear. But what this is doing is it's saying values pointer, which is an address of the first element in the array. It's adding 3 to it. And so it's going to actually add for each bytes for integers. It's going to multiply the bytes times the integers. But this is essentially going to point to the index 3, the fourth element in the array. So in the expression asterisk values pointer plus I, that can be used to access any value contained in a value array. So if you understand this expression, you can add anything to I and it will point you to a specific element array. So if you want to set values index 10 to 27, all you have to do is if you are using a pointer, say values pointer plus 10 and then dereference it and say equal 27. So you see the difference syntax here. Again, it's a notational convenience, but it's also more efficient in terms of the program itself. So pointer, because they are so closely related to arrays, you can easily access elements by just incrementing, decrementing pointers or adding values or subtracting values from a pointer. Very, very useful. To set values pointer to point to the second elements of the values array, you can apply the address operator to value and assign the results to value pointer. Now that we understand the relationship between arrays and pointers, this concept is going to be easier to understand. We say arithmetic, but we don't really, all it really means is you can do either plus or minus or incrementation or decrementation on a pointer itself. So the real power of using pointers to arrays comes into play when you want to sequence through the elements of an array. You want to go from the first elements to the end, you want to iterate through them. This is the real power pointers, because pointers point use addresses each element in array just another address. So you can just do plus plus or on pointers and you can go to the next address. So here values pointer can be used to access the first integer of the values array. It can be used to access values index 0. So if you remember, values pointer is a pointer that's pointing to an integer array, and we assigned it to the first element in the array by just assigning the pointer to the array name. We could also use the address of operator index 0 if we wanted to. But when we dereference values pointer, because it's pointing to the first element in the array, it's going to give you the first integer in the value index 0 array. If you wanted to reference value index 3 via the pointer variable, all you have to do is add 3 to the values pointer and then apply the indirection operator to dereference it. So you could just do something like this. You can say values pointer plus 3 and then dereference it with the asterisk. And you usually put the asterisk outside of quotes to make it clear. But what time is doing, it's saying values pointer, which is an address of the first element in the array. It's adding 3 to it. And so it's going to actually add for each byte for integer. It's going to multiply the bytes times the integer. But this is essentially going to point to the index 3, the fourth element in the array. So in the expression asterisk values pointer plus I, that can be used to access any values contained in a values array. So if you understand this expression, you can add anything to I and it will point you to a specific element array. So if you want to set a value index 10 to 27, all you have to do is, if you are using a pointer, it's a values pointer plus 10 and then dereference it and say equal 27. So you see the different syntax here. Again, it's notational convenience, but it's also more efficient in terms of the program itself. So pointers, because they are so closely related to arrays, you can easily access elements by just incrementing, decrementing pointers or adding values or subtracting values from a pointer. Very, very useful. To set values pointer to point to the second element of the values array, you can apply the address operator to values index 1 and assign the results to values pointer. We saw this. This is just another way to do the same thing I mentioned earlier. If you want to use the address in subject operator, you can always do this if you want, but it's much more convenient to do pointer arithmetic. If value pointer points to value index 0, you can set at the point of values of 1 by simply adding 1 to the values pointer, and this is really what we are getting at with point arithmetic. All you have to do is say values point or plus equals 1, and now values pointer is pointing to the second element in the array or the first index. Very, very nice notation, very easy to do. So this is perfectly valid expression in C and can be used for pointers to any data type, whether it's an integer, character, or anything. And you probably should be thinking about how useful this can be in characters. If you have a character pointer, you can now access each element, each character in a string by just doing a plus plus on a pointer. The increment and decrement operator plus plus and minus minus are particularly useful when dealing with these pointers, because you will usually want to go from one element to the next and so forth. It's not as common to add 22 or minus 20 because you are usually going in sequence. So using the increment operator in a pointer has the same effect as adding 1 to the pointer. Using the decrement operator has the same effect as subtracting 1 from the pointer. So saying plus plus values pointer is going to set the values pointer pointing the next integer in the values array. Minus minus should be values pointer is going to set the values pointer pointing to the previous integer in the values array. But you want to be careful when you are at least in the array and you are not at 0. And the same goes for plus plus. If you are at the end of the array, you don't want to have any out of bounds error. So make sure that values pointer, if you are decrementing it, it was not pointing to the beginning of the values array initially. Another example here, we are actually going to sum all the elements in the array. You see that we have an array sum function, and the function takes an array and it also takes a constant integer as parameter. Inside the function, we are going to create an integer. We are going to initialize that integer sum to 0, and we are going to create an integer pointer, a pointer to of type int. We are also going to create a pointer that's constant. So what that means is you can't change the address of it. It's always going to be array plus n and it's going to be named array, and we are doing this because it makes our loop more efficient. If we set it up to go to the array and just look at the pointer, so array end is pointing to the address of the end of the array. We can say array, which is what passed in the end, then n is the size of the array. Now the for loop is going to initiate the loop control variable pointer which is a pointer to the array, and all you have to do is, if you want to assign a pointer to the first element of an array, all you have to do is say pointer equals array, and then our loop exit condition is if the pointer is less than the array end. Remember, a pointer is an address and the array end is also an address. So we are saying if the address at pointer is less than pointer n, then we want to execute the body of the loop. Pointer is just an integer, it's a hexadecimal address. Each time we increment, it goes to the next address. We have the ending address. So we can say go through the loop until we hit the end. And then we are incrementing the pointer itself, which is going to increment the address to go to the next element in the array. Essentially, because that's what we are pointing to. Then we have inside the body of our loop, we say sum plus equals pointer. We are dereferencing the pointer to get the value, because remember, we want to get the value, we don't want to get the address of the pointer, or the address of the pointer is pointing to. And then at the end, very end, we return the sum. So this is going to sum all the elements in an array. You will notice in the main, we also did a declaration of the function in the there as opposed to the top of the file. I usually like to put them at the top of the file. But in the main, we create an array of 10 elements, 3, 7, 37, -9, and so forth. We then pass in the array or a sum, and we specify the size as 10. And what you are going to notice is it returns the value, which is the sum of the array. So it's very, very nice to use this point arithmetic to iterate through an array. We can just plus to the next address and also look at the ending address to jump out. This is more efficient with the pointer looking at the ending address as opposed to a counter looking at less than n. And you also notice we created them as constant because the constants don't change, and that's more efficient with the compiler. The array here is a constant pointer, meaning that the address cannot change. You also should have noticed in this example that to pass an array to a function, you simply specify the name of the array. So we know how to pass, raise the function, and to produce a pointer to an array. And you only need to specify the name of the array. We saw that when we assign the first element of the array to a pointer, so what this implies is that the call to their array, some function, what was passed to the function, we actually a pointer to the array values. And this really is telling you that arrays and pointers are very, very closely related, that an array is nothing more than a pointer. And this explains why you are able to change the elements of an array from within a function. Because up until this point, when you pass in data to a function, that data does not get changed outside of that function unless it's a pointer. Because that's why we have to pass in the address for the scanf. The only way that elements get changed outside of a function are if you are passing pointers to a function, and because the elements are modified inside that function, this implies that you are passing a pointer. And this is just again providing that when you that arrays and pointers are very, very similar, in that arrays are indeed pointers, just using different syntax. We are going to talk about how we can pass by reference, or really passing a copy of a reference, which will allow you to change data in a function outside of that function. If you remember from one of our previous challenges, whenever we want to change data in a function, we had to use a global variable, because we didn't understand the concept of passing by reference, and we did not understand the concept of pointers. But I mentioned earlier to one of the advantages of pointers are that you can now change data inside of a function and it will get reflected outside of that function. But That's another lecture, but that concept in itself, because of the previous example, is demonstrating how arrays are essentially pointers. So you might wonder why the format parameter inside the function is not declared to be a pointer. Well, it could be. We could just do something like this: int array sum, int star array. We don't need to declare that as an array. It's perfectly valid because arrays and pointers are the same, that we can say int star array. We mentioned that they are really closely related. So you can declare an array type to be a type, can declare it as a pointer to int. And that's why you see many functions that accept arrays as parameters, as arguments, where the parameters are actually pointers. So if you are going to be using index numbers to reference the elements of an array that is passed to a function, then declare the parameters as an array. Again, notational convenience, it's just a different way of the notation, either using the brackets and subscript or using a pointer. The array itself is usually easier to read in terms of maintenance of the program. It more correctly reflects the use of the array by the function, but the pointer is easier to use. If you are using an argument as a pointer to the array, declare it to be of type pointer in the formal parameter. So here is an example with the pointer notation of the function, where the previous example was using an array notation. Here we just say int start array, and what you will notice is the function immediately becomes a lot smaller because we don't have to assign the pointer to the array to the first element like we did. The loop also becomes a lot smaller because we don't need to do that assignment in the first statement. We can just say until the array is less than array end, and we can increment the array, so it's a little less code. It's still very clear what's going on. Hopefully, if you understand arrays and pointers, we are passing in int star array, and we don't have to initialize that array anymore because we are passing it in the pointer. We don't initialize the pointer anymore, and then we are actually setting the address of the end of the array to a constant pointer, array end. We use that to jump out of the loop, and we just say sum plus equals star array using the indirection operator to dereference the array, again returning the sum. And then the main function is exactly the same concept, the same, except the declaration is now a pointer as opposed to an array. So here are two examples using different notation, but providing the same functionality. And that's why you see a lot of pointers as parameters inside of a function parameter. So to summarize, here are some things that are valid when you use pointers and things that are not valid. So if we declare some variables here, we declare an array called arn, and it's contained 3 elements, and then we declare 2 pointers. Now, on those pointers, we can do arithmetic. We can say pointer 1 plus plus. We can say point or 2 equals point or 1 plus 2. We can even say pointer 2 equals and plus plus. It's perfectly valid to do that because you have pointers and you are modifying the pointers by the address. So you can do point arithmetic. You can't do point arithmetic on arrays. So you cannot say and plus plus. You cannot say point 2 plus 0.01 because those are addresses, and you are not actually pointing to anything inside of an array, and you can't multiply arn times point or 1 to get point of 2. Those are invalid. So pay attention to the correct syntax for pointer arithmetic, and also understand that point arithmetic can only be applied to pointers, not arrays. Also, functions that process arrays actually use pointers as argument, you have a choice between array notation and pointer notation for writing array processing functions. So if you are going to process the random function, it's perfectly fine to use a pointer as a parameter. You can choose which one you want to use, but using pointers is usually less code and more efficient. Using array notation makes it more obvious that the function is working with arrays. And array notation has a more familiar look to programmers that have some programming background in certain languages. So if you program before and Fortran and Pascal and so forth, you may use the array notation. Other programmers might be more accustomed working with the pointers and might find the pointer notation more natural, just makes more sense. It's close to machine learning using the point arithmetic and the pointer notation with some compiler. It leads to more efficient code. Another reason to use it. So let's take a look at these examples inside code blocks. So here are our examples from the slides. We have our function declaration up on line 3. It's an array sum. And in this example, we are going to use array notation. So we are going to use the brackets when we use indexes, and we are going to call it passing in the values array and passing in the size. So the array sum function takes an integer array. Well, first thing you need to do is you have to create the pointer that you want to use for point arithmetic on line 14. Then you have to assign the end of the array to the address array plus the size. That's the end of the array, which you can now use to exit the loop. But if we have to assign the pointer to the array, we know that we can assign arrays to pointers to point to the first element by just using the name of the array. We don't have to use the address of operator. We could, if we wanted, we could actually do something like this, and this is fine as well. And then v plus plus the pointer, we are incrementing the pointer because all that's doing is incremented to the next address. It's pointing to the next element in the array, and then on line 18, we are dereferencing the pointer to calculate the sum equals sum plus the value of the pointer that's it's pointing to. So if we build this, we do have one warning, which is main is not an int. We want to change this because it's good to return error values from the main and just say return 0. You could return if there was an error in main, you return a -1. Now we run this, you will see that it just perform the sum of the values in the array, which is 3 plus 7 plus -9 and so forth. Not even sure that this is, but it look like it's 21. Now we can easily modify this array parameter to take a pointer by just declaring the asterisk before the pointer. We call it the same way, we just modify, we don't need to declare the pointer anymore. We probably want to change the name to make it easier, but we don't need to declare this pointer anymore. We still want to get the end of the array, and we don't need to assign it anymore either. We can just have an empty thing there, and it might actually be more useful to have a while loop here. But if we have no assignment, we can just put the semicolon there. And now we are good. We still want to dereference it and we still want to return it. But if we build this, we want to make sure that we define the function declaration as a pointer since we changed it. And this can be any name, but will just be consistent. Now we want to make sure that we are again using all the variables that we changed. So now we built Successfully we run it, and you see you get the same result, which is 21. You understand this difference between using pointers as formal parameters in arrays. You can use them interchangeably. It's just a notational convenience, but you have less code usually when you use a pointer, and you can manipulate it more and you can do more powerful things. It's usually more efficient to based on the demonstrate this concept. It does a good job, and if you understand this example, you are going to have no problem with pointer arithmetic. So the first example that I wanted to show you is the effect of adding an integer value to a pointer. So when we do pointer arithmetic with addition, we can actually see how it works in terms of the addresses. So here in this program, all I am doing is creating a string, a character array. It's called a string, and then I am creating a character pointer called p. I am going through all the entire length of the string, which is multiple. So I am going through the entire array. Just name basic for loops, strength, length of multiple size and multiple, and then I am printing out each actual string or character inside that array. And also what I am doing that I am displaying that address, and then the address with the actual number, then I added to it. So let's look at just the output of this, because the output demonstrates a really good example of pointer arithmetic. So let's go to code blocks and run this. So here we are in code blocks. I clean up the code a little bit. I use str length, set a strn length because it's extra include, and I want to just run this. So when I run this, what you will notice is it's showing you how remember what memory looks like, and it's showing you the values doing the pointer arithmetic. So if you say multiple index I, remember multiple just contains a string, but if we look at this and we say look at the array contents, multiples of 0 is a multiples of 1 is a space, and then the rest are strings. That's the array. Right next to this is the same as adding 0 to the pointer and dereferencing it, adding 1 and adding 2. And it shows you how you can do pointer arithmetic by dereferencing the pointer arithmetic itself and adding numbers to it. So the pointer plus 7 dereferencing, what you get G. Then in the third column, I am showing you the actual address as we increment. So the address of each element in the array using the ampersand just on the character array. We see the address 060FEFF for element 0 and so forth. And then we look at the addresses. If you just add to the pointer itself without dereferencing it, and you will see the addresses line up. And so then we can look at the syntax to see what's going on here in terms of the first thing that we actually display is the index in the array, which is just a counter. And then we display a %c, which is the character at the array. The next thing we are displaying is dereferencing the pointer plus I. So here what we are doing is we are displaying I, and then we are displaying the dereference of pointer plus I, the actual value. So we display as the D just the actual counter, and then point C is we our differencing. So P is our pointer. We are just saying P plus I pointer arithmetic, and then we are dereferencing it, and then to get the addresses, all we need to do for to get the array address is say ampersand multiple, and then the index to get the address of the pointer. Here we just say P plus I to get the actual counter, which is showing you how we are incrementing that P. We just do a P plus percent %D, but it does a good job of demonstrating the various ways that the memory that we are pointing to the addresses are actually displayed and how they are equivalent to the different indexes in an array and the actual pointers. I thought this did a good job. I want to look at one more example that does not another good job concerning pointer arithmetic with longs, because here these are integers. So all we have to do is add one and automatically goes up to the next byte and so forth. Let's look at what we do. We do longs. So in this example, I wanted to also just demonstrate how you can do the same thing with a long and a long pointer with the character pointer. It was just a string character array, but even for long arrays which are different sizes, we can still iterate through them using a pointer. And you can see how the number of bytes actually changes. So even though we say we have a long pointer and we add 1 to it, we are actually adding 4 bytes to it, because the long is a little bit bigger, and we'll see that in this example. So now let's run this example in code blocks. So here's our example. Again, we have an integer counter, a loop counter, we have a long array. We are specifying L by putting the suffix on, then we specify there is size. Again, because it's an array, we don't have to use the address of operator. We are going to go through the entire long. Here we can't use str length, we have to use size of, and we actually have to divide it by each spot in the array. So the total size divided by the single spot in the array, that's when we want to jump out, because these, remember, are our addresses that are incrementing by 4 bytes each. And again, what we are doing here is we are just displaying both the pointer versus the array and showing you how they are related. And then we are displaying the actual total number of bytes that the long is on our system. And so this again just demonstrates how arrays are related to pointers. So if we run this, we are going to see similar output, but what's a little different here is the address size going up by 4 bytes. So we are going to print out the address and the pointer. So for the address and the pointer plus 0, that's going to be equal to array index 0, which is address 6356729. And to dereference the pointer, we'll get the value of 15. So P plus 0 is still going to be equal to the array index 0. And then again, we do the same for P plus 1, P plus 2, and P plus 3. All equivalent to the correct spots in the array for the index. The addresses are going up by 4 bytes, but we can still just add 1, 2, and 3. And we see that the values are the same. And then it tells us this long occupies 4 bytes, and that's why the addresses are going up by 4. What's significant here is we can still add 1 to it, and the compiler knows to go to the next address. So whether we have a long or a character or whatever that particular data type is inside of the system, adding 1 or 2 is going to add the correct number of bytes. So just another cool example I wanted to show you, because this pointer arithmetic is really important and really useful when creating or traversing an array. It makes much clearer and much more efficient. Welcome back. Now that we understand pointers a little bit more detail, I want to talk about character pointers, mainly how you can use character pointers to represent strings. Strings are character arrays, multiple characters, words. So we now know how arrays relate to pointers in the concept of pointer arithmetic. Very useful concept. Strings, because now we can easily traverse a string character by character. One of the most common applications of using a pointer to an array is as a pointer to a character string. The regions are one of notational convenience and efficiency. So using a variable of type pointer to char to reference a string gives you a lot of flexibility. So you are going to try to use character pointers as much as you can over character arrays, specifically using character pointers to pass data to a function, all sorts of nice things like that. So let's look at an example that uses an array to copy a string. In this example, our array parameter is going to be a character array. You will see that right in the function declaration. I want to compare this to a function that takes a character pointer and show you how the character pointer function is a lot more efficient. So in this example, we have two functions, one that takes an array and one that takes pointer. In the first function, copy string, we can go through the entire array using a for loop I equals 0 from index I, and we all go all the way until we see the null character string, and then we increment our loop control variable, and then all you have to do is say to index I equals from index, we are doing a direct assignment there. And then at the very end, after we have gone all the way until we see null character, we add a null character to the end of our array. Pretty basic. Now let's see how sorry, how we do it when we use pointers. First, we declare to pointers as the function declaration in the copy string by just saying char star to char star from. In our for loop, we don't have to actually declare any variables because we have pointers. And we just want to iterate until the from hits the null terminator, and then we can increment both the from and the to pointers, because here we are doing pointer arithmetic. We are just adding one to the pointer, which is increasing its address by one, which is getting the next character, and the next for loop line we just dereference both to and the from, because we want to assign the actual value that the pointer is pointing to, the actual character to the pointer. And then at the very end, we add the null character to wherever the two pointer is pointing to, which would be at the end of the last address of the string or from, but now pointing in the to address. It does not look too bad. I mean, you have a for loop, you basically have the same amount of lines of code, but you see the difference in syntax. You don't use subscripts and you use pointers, use the asterisk. Again, really an issue of notational convenience. You don't see a big advantage here, but you can actually optimize this more to even get down to less code when you use the pointers. So if you have a char array as a pointer, if you have an array of characters or the text, you could similarly define a pointer to it and use the elements in the next text. So here we could say char star text pointer. That's how you define a character pointer. If the text pointer is set pointing to the beginning of the array of chars called text, then you can just increment it by 1. Using these pre and post implementation and decrementation operators, so this above this plus plus text pointer is going to set the text pointer pointing to the next character in the text, which is text index 1. So if we want to look in the next array, just like for integers, all we have to do is add a 1, 2, and we can get the next character. It's much more useful through an character array because you can easily manipulate characters one by one. If you do a minus minus text pointer, which is the discrimination operator, that will set the pointer to the previous character in the text. Because if it is yes, so you will have these three underbounds error. If it was doing a plus plus to the end of the string, you had have an out of bounds error. You always have to be careful, just like an integer arithmetic, to not go past the bounds for an array, but very simple. It relates very closely to when you do integer pointer arithmetic. Character pointer arithmetic is the same thing. It's just even more useful because now you can actually look at individual characters without using a subscript. So if we look at that previous example, and we can actually optimize it a bit more using pointers to make it even less lines of code. So now in our copy string, we do this function. Declaration is the same as before. Create a couple pointers using the asterisk, but we don't use a for loop anymore because it was kind of pointless to use for loop in the previous example because we didn't actually need to initialize the loop control variable. All we need to do is exit a loop on a condition, and then we are actually using the incrementation and decrementation operators in the for loop, but we don't even need to do that. It actually becomes very even much simpler here because if we use a while loop, all we have to do is look at the while loop and it will jump out if it's pointing to a null character because the null character is actually equal to 0 and the while loop, remember that booleans in C are represented by integers. 1 is true and then 0 is false, or really 0 is false and then anything else is true. In this case, null character 0, which is false, it's going to jump out. So all you have to do for the exit condition in the while loop is put an asterisk from what is that doing, that's dereferencing from to see what the value of that character is. So when we are to the end of the string that we want to copy from, we jump out. Otherwise, we just actually put our modification of our pointers right in there. 2 plus plus from plus plus, and now this is post incrementation operator. So what this means is the plus plus is on the right hand side of the variable. And when you do this, it means that you don't add 1 to it until after the statement is done. So what this is going to do, it's going to say star2 equals start from, and then after that statement is done, it's going to add to 2, 1, and it's going to add 2 from 1. If you had the plus plus before the variable name, it would add to that variable before it execute that statement. And that would be a problem because we have missed essentially the first element being copied in the string, but we don't need any more lines of code. We are doing an actual incrementation, pointer, arithmetic, and assignment in the same statement. So we reduce the code by 1. Again, the notation is very simple. We are doing an integer arithmetic assignment very easily. And then at the end, after we are done copying all the strings, we just add to the end the null character to pointer, which we dereference, because the 2 is actually why it does throw the loop. It will be pointing to the last character. So it's just a little cleaned up a bit here. It shows you the power of pointers and how you can use pointers and arithmetic in the same lines. And with these incrementation and decrementation operator, these plus plus and minus minus, it make it even quicker and easier. So it's more efficient as well. If we wanted to use these copy string functions, we could just create two character arrays. We can pass the character arrays directly to the copy string because the zero character arrays are pointers. They are pointers, so we don't have to actually dereference them or add in addresses or anything. We could just say string 2, string 1, and so what this is going to do is it's going to copy a string to be copied to the string to character array and then print it out using printf. I wanted to go through an example of how you can use character pointers instead of character arrays and why they are sometimes preferred. We mentioned that it's sometimes programmer preference where if you have programmed in a previous language like and welcome back. We have another challenge for you. In this challenge I want you to learn all about our pointer arithmetic. Remember, pointer arithmetic is a really neat concept. It's a notational concept, but it's really illustrate how arrays are related to pointers. You can traverse an array very easily with a very simple syntax that reduces your line of code, and it's really neat concept. So you are going to learn all about pointers arithmetic. We are also going to learn more about the constant modifier. So in this challenge, I want you to write a program that tests your understanding of pointer arithmetic and the post modifier. We have learned about both of these concepts in previous lectures. So I want you to write a function that calculates the length of the string. The requirements are the function should takes as a parameter constant char pointer. A constant char pointer means that you cannot change the value of what the pointer is pointing to, and you are not going to do that with the length. A function can only determine the length of the string using pointer arithmetic. I do not want you to use the str length function. I want you to use pointer arithmetic, and the way that I am envisioning this function to be implemented is that you are going to get the address of the end of the pointer. That would be the length of the pointer essentially. But the way that you can get the address of the last string and the pointer is you can write a while loop. The while loop can go all the way to the null terminator character or the null terminator character. Remember, that's represented as int. So the null terminator is actually a 0. So you could write a while loop, and all the while loop has to include in its condition is dereferencing the pointer. Because if the value of the dereference pointer is 0, jump out of the loop, and that would be the null terminator. So I want you to go through the entire pointer, and while you are going through it, keep incrementing that pointer. So now you have a pointer that's pointing to the end of the string. Then to actually calculate the length, all you have to do is minus 2 pointers, the pointer that was passed in, which is the beginning of the string, and then the pointer that you created in the function, which is pointing to the end of the string. If you minus the end of the string pointer from the beginning of the string pointer, you will have the length of the string. So you will be doing pointer arithmetic by incrementing the pointer one by one to get to the ending address, and then you will be using point arithmetic to subtract each pointer. This is really probably the most valid way to use pointer arithmetic for subtraction. You usually don't add two pointers because why would you add two address? You may subtract two address to get how far away two elements are in an array. That would make sense, but adding will not. So just to reiterate, the function can only determine the length of the string using pointer arithmetic. Create a local pointer in your function, increment that pointer each time to get to the end until you see null terminator, simple while loop, and then once you have the ending address, you already have the beginning address. Subtract those two pointers, that will give you the length. You should return that length as an int from the function, and then you can just print out the actual length itself. So this assignment is getting you familiar with the pointer arithmetic and also how to use the constant modifier, because you don't want to change the actual value that it's pointing to, and subtracting two pointers as well, and also using a while loop where you can look at the pointer's value itself. In this lecture, I want to talk about a concept called pass by reference. When we first started talking about pointers, I mentioned one of the advantages is you don't have to use global variables as much, because when you pass a pointer to a function, the function can use that parameter, and when it modifies that parameter, the data will be modified outside the function. So this is a very valuable concept. We are going to talk about this. This is more of a concept. C actually does not employ this, and I'm going to show you how and give you some examples, basically how this works. So there's this concept of pass by value. This has to do with the functions. We talked about passing data to a function, but how is it actually passed in terms of the language in the compiler? So there's a concept of pass by value. And this is what we have been talking about until now. Whenever we call the function besides the scanf function, but every other time we call the function, when you modify that data inside the function, it did not get modified outside the function. So we talked about local variables. That's kind of a different concept. But when you pass data to a function, there's two ways you can pass it. You can pass it by value, you can pass it by reference. C does exclusively passing by value, and so does Java. All pass by value, but it simulates pass by reference because you copy addresses, and so even though this concept pass by reference is not actually employed by C, it stimulates it. And so to understand what pass by reference means and why that's important, we are going to talk about that. But pass by value is when a function copies the actual value of an argument to the formal parameter of the function. And this is why if you have an integer, a float, or a double, and you pass that in as an argument to a function, that actual variable does not get modified outside the function because it's copied. So changes made to the parameter inside the function have no effect on the argument. The argument being passed in does not get modified, so it almost acts like a local variable because it's a copy. How it's actually happening under the hood is it's being copied and passed to the function. C program uses call by value to pass arguments. Everything is called by value, passed by value. These are used interchangeably, these terms. So again, this means the code within a function cannot alter the arguments used to call the function. There are no changes in the values, though they had been changed inside the function. It seems like they are local variables. And that's why earlier up until this point, when you go to create global data, if you wanted to share the data from one function to the next, and this is how C works. But what happens when you actually pass in a copy of an address, that it can mimic pass by reference, But here's an example of how we have been using pass by value. It's demonstrated very nicely here. This swap routine is an often used case to demonstrate pass by value, because what it does is it creates a temp and it swaps the parameters. The arguments are being passed. So if we have a function called swap that takes two integers, we create a local variable temp. If we assign to the parameter x to temp, temp is going to be equal to x. If we say x is equal to y is now going to be equal to x. If we say y equals to temp, y is going to be equal to temp. But when call this function, passing those values x and y is going to be local to this function. Those variables are not going to be modified outside this function, and this function demonstrates it very useful because we are assigning to y and we are assigning to x. And x and y is local to this function because we are passing by value. They do not get modified outside this function, and that's why we have to use global variables. But they are integers. They are two integers, x and y. They are not addresses. They are integers, and that's significant. So if we call swap and we see what this is looking like, you are going to notice that the values do not change. So if we create a variable called a 100b with 200, and we print out the variables before we swap 100 and 200, then we call swap. The variables are not going to be changed after we print them out again. So let's look at this in code blocks, and this will demonstrate pass by value. So here is our example. We have our swap routine. We are swapping values of data that's passed x and y. We are calling it with 100 and 200. We are going to print out before we call the function. We are going to print out after. And what you will notice is the variables a and b never change. And the reason for this is because we are doing pass by value. So if I run this program, we can see that before swap, the value of a was 100. After you swap the value of a 100, and the same for b, 200 and 200. And the reason for this is because we passed by value. If we passed by reference, those variables a and b would change after the call to swap. Now, how about if we employ this same technique, pass by value, but we copy pointers? What do you think is going to happen? So pointers and functions get along quite well together. You can pass a pointer as an argument to a function, and you can also have a function return a pointer as its result. We are going to show how to do that as well, but pass by reference copies the address of an argument into the formal parameter. The address is used to access the actual argument used in the call. So what this means is that changes made to the parameter inside the function after the affect the argument that's in the call. And so even though it's not technically under the hood passed by reference, it mimics or simulates passed by reference. We are copying the address. If you copy the address, you have a new address and memory for that value, the address. But if you try to assign to that address, it's going to assign to that. So even though it's passed by value, it's copying. And if you are copying a regular integer, you don't make changes. If you are copying an address, so to pass by value by reference, argument pointers are passed to the function types with the asterisk. Changes inside the function are reflected outside the function as well. You don't have to use global variables as much, unlike a call by value, where the changes do not reflect outside the function. We are still copying, we are still passing by value, just the value of a copy of the address. So this is important concept to understand. Now we create our swap function. We are going to create with the declaration inside the function as a strict star and star. That's saying that this function takes pointers. Now when we assign inside this function, we have to actually use the indirection operator to dereference, because we want to assign the values. We are going to assign the values that is that x points to the temp. We are going to assign the values of x points to the value that y points to, and then we are going to assign the value that y points to temp. Temp is an integer, so we don't have to dereference it. Now when we invoke it with 100 or 200 by passing in a and b, a and b are not pointers. So we have to pass in the address, because the function takes pointers. Whenever you have a function that takes pointers and you don't declare a pointer, you have to use the address of operator, and it's the same thing as how we use scanf. But now you are going to notice when we invoke this, after the call to swap, the variables a and b are going to be changed. They are going to be swapped. A is going to be 200, b is going to be 100. So now let's look at this example with our swap method. Change to pointers in code blocks. We are in code blocks. We modified the swap function to take pointers. So we have to dereference them with when we assign them. We also now pass in the address of a and b, because these are now integers, and the swap now takes pointers. So when we run this, we are going to see that the call and after is now going to be changed. So before we call swap, a is equal to 100. After we call swap is 200. Before we call swap for b, it's 200. Afterwards, it's 100. So we are able to change the value of variables inside the function, because we are making a copy of the address. Very, very important. And one of the big advantages of pointers. So let's summarize the syntax. I already did, but let's go through in more detail. You can communicate two kinds of information about a variable to a function. You can transmit the value of x, and the function must be declared with the same type as x. We know that whenever we pass data to a function, we have to pass the same types when we call it. And here we have int function, want to invoke it, and it's defined as an int num. So when we transmit the value of x in the function, they have to be declared with the same type. And then if you want to actually invoke an address of x, it requires the function definition to include a pointer to the correct type. So whenever you use pointers, you have to make sure that if you are passing data and the data is not a pointer, you have to get the address of it. What this is summarizing is, if you define a function that does not take a pointer, you can just call it and pass in the data. Make sure it's not a pointer. If you have a function that does take a asterisk pointer, when you invoke it, you have to invoke it with the add or index operator. You have to pass the address, and that's the syntax. Now you can also qualify a function parameter using the constant keyword. This indicates that the function will treat the argument that is passed in for this parameter as a constant. It's only useful when the parameter is a pointer, because if you are passing by value and you are not passing in pointers, it does not matter because it's not going to affect the change on the outside the function. So why would you make it a constant? Who cares if you change it? The only reason you make a pointer constant is because you don't want to have outside the function values changing, and so you can apply the constant keyword to a parameter that is a pointer to specify that the function will not change the value to which the argument points. Very important. So in this example, we have a send message function. It takes a p message pointer. We put the constant keyword before the char star. So this type of parameter p message is a pointer to a constant character. It is the character value that's constant, not its address. So in this case, what we are doing is the pointer that's being pointed to cannot change. We can change the address, but we can't change what it's pointing to the value. The syntax is similar to when we create constant on other pointers. The constant keyword is it's the first thing showing, then you can't change the value. Now, you could specify the pointer itself is constant, but this makes little sense because the address is passed by value. You cannot change the render pointer in the calling function. So this is just if you try to make it so that the address could not be changed. What's the point? Because it's passed by value. So you are actually making a new memory location to hold that specific address. So if you change it, who cares? It's not going to change it on the outside. You only want to be able to make the parameter a constant so that you don't change the value of what it's pointing to. You can't change the original pointer and the calling function anyways because it's passed by value, passed by copy. The compiler knows that an argument that is a pointer to constant data will be safe. So there are advantages to this. You can't accidentally modify what the value is pointing to. So you might do this again if you don't want the changes to be reflected on the outside of the function. If you pass a pointer to constant data as argument for a parameter, then the parameter must be used to like in the above. When you invoke the function and you pass it into constant, then you have to pass the function declaration and also take a constant character pointer just like normal other pointer that are constant. They have to be defined and the defines have to match the prototype. Returning pointers from a function, returning a pointer from a function is a particular powerful capability. It provides a way for you to return not just a single value but a whole set of values. So again, one of the other advantages I mentioned above pointer is that you can now return more data from a function. In the past, you can only return one value, but with a pointer, because a pointer could be pointing to a structure which we have not talked about yet, or even other things, you can return multiple values. So we know how to pass pointers to function. Now we want to talk about returning pointers. You have to declare a function returning a pointer, so the function declaration has to match up. It's very easy to do that. You just say use the asterisk when you declare the function or define it and have the return type for that pointer what it's pointing to. So be careful. So there are specific variable that the argument points to. It is somewhat problematic when you are returning pointers because if you modify that pointer inside the function and then return it, it could be something that you don't intend it to do. So always use local variables if you do not want to affect a variable that your argument points to. And so this lectures describe how you can pass pointers to function. and how you can return pointers from function. And by using the mechanism of passing pointers to a function, it demonstrates or mimics pass by reference, because you are copying in an address, and when you copy an address, if you write to that address, you are going to update whatever is pointing to that address, which actively means that you are changing the value of the data inside the function. It's going to reflect it outside the function. We use the swap routine to demonstrate that this is a very powerful concept, and you want to mimic pass by reference. You can use pointer to do that. You can want to do that when you want to change things outside the function. To be on pointers, what I want to try to help you learn in this challenge is the concept of pass by reference. So even though C is doing everything passed by value, it's actually making a copy of an address when you use pointers. So mimics pass by reference. And the big advantage of pass by reference is that when you change a pointer's value or variable inside of a function, you are going to see the change reflected outside the function. So we don't have to use global variables as well. And it's big advantage to be able to pass in data to a function as a pointer that mimics pass by reference. So in this example, you are going to write a program that tests your understanding of pass by reference and how to use pointers to do this. I want you to write a function that squares a number by itself. The implementation of the function is going to be quite simple. It's just going to square the number that you pass in. So the function should define as a parameter an int pointer. In your function declaration, it takes an int star, which is a pointer. And then inside your function implementation, all you are going to do is you are going to need to dereference the value of the pointer and multiply it by itself. You don't have to return any data from this function. I just want to let you understand the concept of passing in by reference or passing in a pointer. The last thing that this program should do is it should print out the value of the variable, the value of the pointer that you pass to the function. So you don't even need to create a pointer to pass in. You can use a regular parameter, data type, and integer float. It's just when you pass that integer float in. It has to be the address, because the function for square only accepts a pointer. But again, what you are going to notice here is that the value or the variable outside the function, the one that's being passed in to the function, is going to change because you are using the address, and this is going to mimic pass by reference. So good luck on this. Pretty straightforward. Again, going to get you familiar with pointer syntax as well as this concept of pass by reference. Hello and welcome back. In this lecture, I want to talk about dynamic memory allocation. This is directly related to pointers. You can only employ this on pointers. So let's get started. So whenever you define a variable in C, the compiler automatically allocates the correct amount of storage for you based on the data type. We have seen this throughout. When we create integers, floats, doubles, you don't have to allocate any memory. The compiler does it for you. It actually allocates some memory. Same goes for pointers, by the way. When you create a pointer, memory is allocated for you, so that it stores a pointer type and address. Now, that does not mean that memory is allocated for that address. Up until this point, whenever we assign data to a pointer, we have always assigned an existing variable. So if we wanted to assign data to a pointer, we have used the ampersand address of operator on a variable. That variable already had memory allocated for it. But what if you wanted to create a pointer and you did not want to assign it the address of operator? You wanted to dynamically allocate memory. That's what this whole entire lecture is about. So it's frequently desirable to be able to dynamic allocate storage while a program is running. Allocate memory as you need it. If you have a program that is designed to read in a set of data from a file into an array in memory, you have three choices. You can define the array to contain the maximum number of possible elements that compile time its fixed size. If you define the array that has 50 elements, it's only going to contain 50 elements. The compiler determine that it's 50, it's going to allocate that much memory when it runs. You can use a variable length array to the dimension, the size of the array runtime. We talked a little bit about these variable length arrays. They are not supported until C11. They are actually taking out C11, they are adding C99. This is where you can put in variables, but these are still sort of fixed size because all that means variable linked arrays, all it means is you can pass in variables for sizes, but they are still static. Or the best choice is you can locate the array dynamically as you need it. And there's different C functions that you can call to do this. So it's going to be very useful to be able to dynamically allocate memory. So with the first approach, which we have been doing all the way up until now, whether it's an array or whether it's a data type, it's a fixed size. You have to define your array to contain the maximum number of elements that will be right into an array. So you would do something like this: int data array 1000. What this means through is the data file cannot contain more than 1000 elements. If it does, your program going to break. So you just have to hope that the whatever file you are reading in does not have a lot of data. Your program will not work with large sets of files or larger files. And if you do want to work with larger files, you have to go back and you have to make the array larger. You have to change the size, but then you have to recompile it in or on all that stuff. It's compiling time. No matter what value you select, you always have the chance of running into the same problem again in the future because it's a fixed size. The size is determined when you compile the code. It does not adjust when you run the program. It does not dynamically change. Using dynamic memory allocation function, you can get storage as you need it. This approach enables you to allocate memory as the program is executing. So think of the advantage of this. First of all, you don't create a ton of memory that you might not use. You are only going to create as much as you need. And if you do need more, you can allocate more. You don't have to go back and recompile and change the size. So dynamic memory allocation is the way to go. Depends on the concept of a pointer, and it provides a strong incentive to use pointers in your code. So we talked about the advantages of pointers, and you may have thought to yourself, well, okay, they are cool concept, but why do we need to use them? This is one of the big reasons, so that you can allocate memory dynamically. And again, what is this? Minus minus C is all about being an efficient language and not using a ton of memory. So C runs on embedded system, real-time programming, and this is one of the reasons why, because you can limit how much memory you use based on the need. So dynamic memory allocation allows memory for storing data to be allocated dynamically when the program executes. Allocating memory dynamically is only possible because you have pointers available, because you have an address and you can change how much the pointer is pointing to. You can readjust the memory. The majority of production programs will use dynamic memory allocation. If you are writing code in C, you are going to use this. Even if you are a beginner, you are going to use dynamic memory allocation. Most useful programs will employ this concept. Allocating data dynamically allows you to create pointers at runtime that are just large enough to hold the amount of data you require for the task, so you are not wasting memory. Vital. We also have to talk about the heap versus the stack. These are two ways that you can store memory in a program. To different data structure, you can store data on the stack or you can store data on the heap. Dynamic memory allocation reserves everything on the heap. We are not going to into detail of how these are recognized, but essentially, when you store data on the heap, it allows for more change. You can arbitrarily change the size of data object, and it sticks around a lot longer when you allocate memory in a heap. It sticks around the entirety of your program. When you use a stack, it's more limiting. Stack is used for everything from function arguments and local variables. That's where everything those are stored, and that's why we talked about the call stack. It looked at methods and function. I use methods every now and then, but methods is really an object-oriented term. So functions, everything related to functions are created on the stack. So what that means is when you execute a function, it gets put on the stack. The local variables get put on the stack. When you exit the function, everything gets deleted. So memory located on the stack does not stick around for very long. That's one of the reasons when you dynamically allocate memory, it's on the heap, because you control when you use it, and when you don't use it, you allocate it and you delete it. It's tough on the stack. You don't control it, automatically gets deleted, automatically gets allocated. So local variables inside functions like the main, those are created on the stack and so forth. The memory on the heap is different. It's controlled by you, the programmer. When you allocate memory on the heap, it's up to you to keep track of when you the memory you have allocated is no longer required. So you have to delete the memory, you have to free the space when it's no longer used by you. And this is very, very scarce resource. Today we have a lot of memory that you can run a computer, 12 gigs, 16 gigs, whatever if it is. But for programs that are embedded running on devices, you don't have that much memory necessarily. So you want to control how much memory you use, and you also want to release the memory when you are done using it. So other applications can use it. Again, more important in low-level embedded type systems, but this is a freedom that many languages don't have. This ability to control your manager memory by the programmer, and it can make the program much more efficient and much faster. So in the next lecture, we are going to talk about how you can actually do this, what functions can invoke. Obviously, there are different functions that you can call to allocate memory into free memory up. Hello and welcome. Now that we understand dynamic memory allocation, we have to implement it. We have to actually know how to do it in C code. So we are going to talk about three really important functions: malloc, calloc, and reloc. You see that they sort of have names where memory allocation, calloc, and reallocation. The simplest and most common way to allocate memory is through a standard library function named malloc. This is allocating dynamic memory at runtime. In order to call this function, you need to include the standard lib header file. You specify the number of bytes of memory that you want allocated as its argument. What's returned from this function is the address of the first byte of memory that is allocated. Because you get an address returned, a pointer is the only place to put it. So this is why dynamic memory allocation is only possible via this concept of a pointer, because it returns addresses. You can only put an address in a pointer. That's what a pointer stores. A pointer stores an address. So here's how you do it. Very simple syntax. Usually when create your pointer, you don't have to You could create your pointer and set it to null. And then in the next line, you could malloc. But here is the standard syntax. You are creating your int pointer to a type int. And then you will notice that you call malloc. And in here, we are saying malloc. We are going to create 100 bytes for malloc, and then we are going to cast it to an int pointer, because malloc only returns an address. You have to cast it to an end pointer because that address is storing an int pointer. This is the standard way to do it. Now you are requesting 100 bytes of memory and assigning it to the address of the memory block to p number. P number is going to point to the first int location at the beginning of the 100 bytes that were allocated. So what this means is, since integer are 4 bytes a piece, it can hold 25 int values. And again, this is assuming that you have 4 bytes. Now, depending on the system that you are running, they may be larger, maybe smaller. So you should see the problem with this. This code's not going to work on different systems because you are allocating based on the assumption of the int size. So it's not really good to use malloc in this manner with a constant number 100. When what you want to do is you want to use the size of operator, so it would be better to remove the assumption that ints are 4 bytes. Instead, if you want to allocate room for 24 integers inside the malloc argument, specify the number of integers you want to allocate and then multiply that by the size of the integers, and this will make the code much more portable. This code will now work on different systems, different operating systems, different architectures. You still cast the return value, the address, because it has to be pointing to a type int. So you say int star. The only difference here is you use the size of operator. Size of operator is really important when you are allocating memory using malloc or realloc. You always use and want to use the size of operator for that type that you are allocating, and then multiply that by how many particular numbers you want. So if you want to store 25 int, so you do 25. So the argument of malloc above is clearly indicating that sufficient bytes for accommodating 25 values of type int should be made available. Also, as I mentioned, notice the cast. This convert the address returned by the function to the type pointer to int and int pointer. Malloc returns a pointer of type void. That's what it makes it so useful. It returns that address, but it's a void pointer. Remember, we talked about void pointers and why void pointers are useful, because now you can have a function that can take different parameters and it can return a void pointer. Now you are seeing the power of returning a void pointer again. But to use it to actually assign data to it, to dereference it, you have to cast it. If we did not want to cast this, we could say void star p number. We don't cast it, but then we would have to eventually cast it once we wanted to dereference it. But that's why we have to cast from malloc. It's returning an address and you want it to point to an int type, and it's returning a void type. You can request any number of bytes. However, it is dependent on your system and how much memory you have on your system. So if you try to create or try to request a ton of bytes, or there's some limitations, it could fail. And when it fails, it returns a value of null. Malloc will return null. And this is good because when pointers are pointing null, it means that they are not pointing to any memory. So you can't correct or change any memory inadvertently. So it's always a good idea after you do a malloc to immediately check for null before you use it. Just like it when you sign data, or just like it when you dereference a pointer. You want to make sure that you are actually pointing to something. So here we are allocating some memory for p number, our pointer, and then we are saying if not p number, remember the null is 0. So you can just use a not on it. You don't have to actually compare it to null. You can compare it to null. It makes it more readable, maybe make it more explicit. But you can just say not p number, and that's actually saying not 1 and null is 0. So this will check for null. And if it is null, that basically means that memory was not able to be allocated. If you are not able to allocate memory in your program, you are in trouble. And so what you should usually do in this code to deal with the memory allocation failure is you should abort, you should call exit, you should get out of your program. Because if your program cannot allocate memory, your program's hosted. So usually this is you call an accident abort if you can't allocate memory. At least when you do this, you can display a message, terminate the program. It's much better than allowing the program to continue when you were not able to allocate memory, because then you you may continue, you may try to use that memory, it's going to be null. So the program is going to be crashed anyways, but you are not necessarily going to know why. You have to look at the call stack. It will take a lot longer to debug that error releasing memory. Now, I mentioned that since you are the programmer is responsible for allocating the memory, you have to get rid of the memory when you are no longer using, because memory is a vital resource, because especially on embedded system you should not be using memory if you don't need it. So you have to release the memory. You always want to release the memory when it's no longer required. Memory that you allocate on the heap will be automatically released when your program exists, which is good because it's does do some cleanup, but it's much better to explicitly release the memory when you are done with it, even if it's just before you exit. It's cleaner. Always do it free or always release the memory after you allocate it. You want to follow this rule. This is a stringent, strict rule. Always release memory if you allocate it. A memory leak occurs when you allocate some memory dynamically and you do not retain the reference, you are unable to release it. Maybe you are out of scope for that reference. You don't release it. That's called a memory leak. There is a memory allocated, but it's no longer being used. This often occurs when you are in a loop and you are allocating memory in a loop. You are in the loop, you allocate this memory, you use it inside the loop, and then you jump out of the loop and you no longer release it. Each loop iteration is allocating it. So to free memory that you have allocated dynamically, you must still have access to that address. So usually you want a free memory when you are done using it, and usually in the method that you allocated it. However, if you are passing that memory to another function and then it's that function responsibility, but usually you want to release the memory, the function that you allocate it to release the memory for a block of dynamically allocated memory whose address you have stored in a pointer. All you have to do is call the free function. This is in the standard lib as well. You just passed in the pointer to the free function, and usually after you pass that pointer, you want to see it to null, because that's saying that you have no memory allocated for it. The free function has a formal parameter of type void star, so you can pass in any pointer type and it will work. You don't have to actually cast it or anything like that. As long as p number contains the address that was returned when the memory is allocated, the entire block of memory will be free for further use. Other programs can use that memory Your program can now use that memory and significant when you are on an embedded system. And then, as I mentioned, you always want to set the pointer to null to signify that that pointer is no longer pointing to anything. That memory has been free. There is another nice function called calloc. This has a couple advantages over malloc. It's very similar to malloc, but what it does is it allocates the memory as a number of elements in a given size, and it also initializes the memory. That's the difference. Initialization. I talked about the importance of initialization. That's why you always want to initialize data so that you understand that there is data in there that you are expecting. When you uninitialize data, there could be a data in there that you don't have any clue about it. So always initialize your data with something, and calloc is little bit better because it does it for you. It takes two arguments, has two parameters, the number of data items for which space is required, the size of each data item. It's declared in the standard lib header. You call it just like you call malloc. Looks pretty much the same way. In this example, we are creating an integer pointer and we are allocating 75 integers of size of int. So it makes two parameter. It's a little cleaner because you don't have to actually do a multiplication in malloc. You had to do 75 times size event. Here you just say 75, you are creating 75 ints and the size for it is 4 bytes or whatever the system returns from the size of operator. But again, the significances of this, it's going to initialize all that data as well. The return value could be null if it is not able to allocate that memory, which in turn you should not abort. But it's very similar to using malloc, except the big plus is this initialization. All the ints are initialized to 0, and that's a really big deal, big advantage. It's also a little bit easier to use with the two parameter. Let's talk about another function called relog. The relog function enables you to reuse or extend memory that you previously allocated using malloc or calloc. So this is a way to dynamically change how much memory is allocated while you are running. So you could initially create so much memory and then you realize that there's not enough memory. Well, what you can do there is you can just call relog, and this will relocate memory. It expects two argument values, a pointer containing an address that was previously turned by a call to malloc. So you have a pointer that has some memory allocated or calloc, and then the size and bytes of the new memory that you want to allocate it. So this will allocate the amount of memory you specify by the second argument. That's the second argument. It's transfer the content of the previously allocated memory reference by the pointer. So it automatically knows how much memory you had previously allocated because you pass in the pointer. And then it will actually add to that the newly allocated memory, and it returns a void pointer to the new memory. So you have to recast it when you call relog, just like the other ones. It returns null if you were not able to relog, which again is probably a fatal error and you should abort. The most important feature of this operation is that relog preserves the content of the original memory area. You are just extending that memory. It may be fragmented because you may not have been able to do it in sequence, but you still have all that memory that you can assign to now data. Let's look at an example. In this example, we are going to use malloc, and then we are going to relog the memory, and then we are going to free it. So here we are creating a character pointer. We are not initializing it to null. We probably should be, but it does not have any memory allocated to what it is pointing to. It has memory allocated to store the pointer. which is just an address. But if you try to go to that address, your program will be host. So what you do is you call malloc. Here we are saying malloc 15. This will create 15 bytes for a character pointer. We cast it because it returns a void pointer. So str is a pointer now that has memory allocated for what it's pointing to. We then can use str copy to pass in some data to what it's pointing to is string, and we print out the string in the address. Well, then we realize that what we allocated 15 bytes is not big enough. So then we call relog and we pass in the pointer which is str, and we want to relog 25 more bytes. Then that returns a void point as we have it casted again. So now we are still going to have in memory session. So now we can call string concatenated, and we concatenated to the string com. So now it's let's be json.com, and then we print it out. And then last but not least, probably the most important thing of this slide, so we don't have a memory leak, is we call free. Always call free when you call malloc. So let's take a look at this example inside code blocks. Here is our code example inside our code blocks editor. And the first thing, first of all, you see our code. This is our code. The first thing you should notice is we are including the standard library header file because that's where our malloc functions and our relloc functions are in, as well as our free function. Also, because we are using some str function, concatenation and copy, we are including string.h. Now on line 8, we are going to create our character pointer. It has no memory allocated for it. We should initialize this to null because it's not pointing to anything yet. On line 11, we call malloc. And we should probably say 15 times the size of char in case the size of bytes of char is different. And then we cast it. Into a character pointer because malloc returns a void. We then copy it. We tried to copy this and we didn't do anything on line 11. Program would crash because we have no memory allocated for what a string points to. We then just print out the string and the address. Now we call relog. We need to store more data than 15 bytes. We are going to relog with 25 bytes, and we probably want to again size of char to be consistent. We cast this and then we concatenate onto our existing memory location that contains json.com, and we are going to print out json.com. And then last but not least, on line 20, we free that memory up, which is really important. So let's go ahead and run this. And what you will just see is that when we print it out the second time, we have the concatenation. So our first string, we have memory allocated and it's an address, this. Then we created a new address by reallocating and taking the existing size of the pointer that we passed it as an argument. So this address, it actually has more data allocated to it, the existing data in JSON and 25 more bytes. And so what you notice is the concatenation work. Because when we reallocated, we put the contents JSON in that memory and we just extended it. So a lot of advantages to using these malloc is calloc and free relloc calls. You want to use these, you want to understand these pretty simple functions to use. So in our last slide, let's just go over some guidelines. You want to avoid allocating lots of small amounts of memory. It's not efficient. When you allocate memory on the heap, it does have some overhead with it. And if you allocate small blocks of memory, it's going to have some more overhead, and then allocating fewer larger blocks. So allocating the memory that you need, but don't do it every statement with reallocation. Do large chunks. Only hang on to the memory as long as you need it. Memory is a scarce resource when it's on the heap. It's even more scarce. So when you are finished with a block of memory called free, always ensure that you provide for releasing memory that you are allocated. Decide where in your code you will release the memory when you write the code that allocates it. Make sure you have access to that pointer. If you need to make the pointer global, then you need to do that. But usually, wherever you allocate in that function, you should release it in that function. If you have other functions releasing memory for you, you are then assuming that not good. There is too much coupling and dependency there. The person that creates it should be the person that deletes it. Don't put the responsibility onto other functions and much. Make sure you do not inadvertently overwrite the address of memory you have allocated on the heap before you have released it. It will cause a memory leak. So if you try to write too many bytes to it, if you have misuse, so be especially careful when you are allocating memory within a loop, because this can cause problem in buffer overflows. I hope this was helpful. Dynamic memory allocation, and understand how dynamic memory allocation works. So you are going to need to malloc a string. It's going to be pretty basic, but it will get your understanding this whole concept of dynamic memory allocation. What are the advantages of dynamic memory allocation? Well, it means that you can allocate enough memory when you need it. You don't have to waste a memory. If you need more memory, you can reallocate. This assignment just going to have you using malloc. So in this challenge, you are going to write a program that tests your understanding of dynamic memory allocation. I want you to write a program that allows the user to input a text string. So you are going to need to use scanf. You can also use git as get as GTS. We have not talked about it at all, but gets or fgets on the standard input stream will allow you to read a string that contains spaces. Remember, scanf. It's not only going to read the string up to a space. If you use gets, you can read multiple strings separately by spaces. Either way is fine, though scanf or gets, either way, you are going to have to use enter a string. The program is going to print the text that was inputted. That may seem very easy, but the difference here is that the program is going to utilize dynamic memory allocation. You can also have the user enter the limit of the string they are entering. And then you can use that for malloc. So you know how many bytes to allocate. You should create a char pointer, only a char character pointer, no character array. I want you to allocate memory. Remember, when you create the character array, the memory is automatically already allocated for you based on what the size that you put in the brackets. And again, a big advantage of that is now what if you try to enter something larger than what you put in the size, you have to recompile its static that memory gets allocated at compile time. Dynamic memory gets allocated when you are running the program. And so you can determine how much memory you want to allocate based on what the user enters. So again, ask the user to enter a number or the number of bytes you want to allocate for the string, then ask the user to enter the string in. And you have to correctly allocate memory, then pass that character pointer into scanf or gets, and then basically just display the text that was entered. And then lastly, do not forget about the all important free function. You always want to release your memory when you are done using it. and you want to make sure you do that so that other programs can utilize that memory. Memory is a scarce resource, especially on embedded system, real-time programs. So don't of the memory, release it. Good luck, and I will provide